SMACS 0723 Deep Field. Over 10,000 galaxies in a single frame. Imagine pointing a camera at a tiny patch of sky no larger than a grain of sand held at arm's length. That's exactly what scientists did with the James Webb Space Telescope when capturing the deep field known as SMACS 0723. In a single frame, thousands of galaxies emerged, some so ancient that their light has traveled over 13 billion years to reach us. This mosaic revealed not only a stunning visual collection, but also critical clues about the formation of the early universe. Each point of light may contain hundreds of billions of stars. What makes this image so special isn't just its beauty, but what it represents in terms of scale. We are seeing the universe as it was billions of years ago, across different stages of development. Some galaxies appear stretched or curved due to gravitational lensing when light is bent by massive clusters of matter. This effect not only magnifies distant galaxies, but also reveals regions previously invisible to Hubble. Webb, with its infrared vision, pierced through dust layers that blocked visible light. Among the visible objects are spiral, elliptical, and even unclassified galactic structures. The morphological variety shows that even within the first few billion years after the Big Bang, the cosmos already exhibited surprising complexity. This kind of image allows scientists to study star formation rates over time, the growth of supermassive black holes, and the large-scale structure of the universe, all captured within a microscopic slice of the night sky. A key technical detail is that this image was constructed from multiple exposures using different infrared filters. This not only allowed for the detection of faint light from distant galaxies, but also enabled separation of wavelengths to build a spectrum for each object. In other words, Webb didn't just take a photo, it measured the chemical composition, age, and distance of each visible point. It's like having an entire library of galaxies condensed into a single image. The exposure time needed for such a capture was enormous, over 12 hours of continuous observation. This highlights how sensitive Webb is to subtle light variations, allowing it to detect objects nearly invisible to other telescopes. The result is not just a beautiful picture, but an immensely valuable scientific tool. Researchers have already begun extracting data to refine models of galaxy formation and cosmic evolution. It's a clear example of how a single image can be worth billions of data points. Viewing this image is like looking through a window into time. We're not observing space as it is now, but as it was billions of years ago. Each luminous point represents a frozen moment in cosmic history, and together they tell a grand narrative about how the universe became what it is. James Webb didn't just capture galaxies, it revealed lost chapters of universal history. It stands as one of the deepest and most meaningful photographs ever taken by humanity. The presence of distorted and duplicated galaxies also enables more precise measurements of dark matter distribution in the foreground clusters. Since dark matter doesn't emit light, it can only be inferred through the gravitational effects it has on passing light. Thus, SMACS 0723 is not just a beautiful scene, but a natural laboratory for studying the invisible. These distortions provide indirect maps of unseen matter. Beyond dark matter, the deep field helps us understand the formation of the first stars. Some galaxies in the image are candidates to host population 3 stars, the universe's very first, composed only of hydrogen and helium. If confirmed, these observations could rewrite fundamental parts of cosmology. For the first time, we have instruments capable of detecting residual light from these early phases of stellar evolution, something unimaginable just a few years ago. SMACS 0723 also served as a test of Webb's spectroscopic capabilities. By splitting the light of each galaxy into its spectrum, scientists can identify elements like oxygen, carbon, and nitrogen. This helps estimate the galaxy's metallicity, how processed they are compared to the primordial material from the Big Bang. The more metallic a galaxy, the more stellar generations it has undergone. This reveals which galaxies are young and which have experienced multiple cycles of stellar birth and death. This spectral analysis also unveils information about star formation rates. Some galaxies in the field are rapidly forming stars, while others show signs of past activity. The variety of evolutionary stages in a single frame underscores the complexity of cosmic history. There is no singular path of evolution. The universe is a patchwork of parallel stories, and SMACS 0723 offers a rich statistical sample of these possibilities. Another impressive aspect of the image is its depth range. Even in a single field, Webb was able to observe objects at different distances, layered across time. This enables the construction of a three-dimensional map of the expanding universe. When combined with computational simulations, astronomers can model how cosmic structures evolved over billions of years. In this sense, SMACS 0723 is like an archaeological cross-section of space. Glass Z13, the oldest galaxy ever observed, formed 300 million years after the Big Bang. The galaxy, Glass Z13, was identified during one of Webb's observation campaigns within the glass field, GRISM Lens Amplified Survey from Space. What astonished scientists was its distance, about 33 billion light-years from us when adjusted for the expansion of the universe. This means we are seeing this galaxy as it was only 300 million years after the Big Bang, a time when the very first cosmic structures were still emerging. It is, so far, the oldest object ever directly observed. Glass Z13 is not a grand galaxy like the Milky Way. It is compact, irregular, and extremely faint, composed of a relatively small number of stars. Still, its existence raises an important question. How could such an organized galaxy have formed so early? Traditional models suggest it should take more time for stars and dust to assemble into recognizable structures. The presence of Glass Z13 forces cosmologists to rethink the earliest stages of galaxy formation. One of the main challenges in identifying such distant galaxies lies in the limitations of earlier instruments. Telescopes like Hubble had already suggested ultra-old candidates, but without the spectral sensitivity of Webb, confirmation was impossible. With its infrared capabilities, Webb can detect the highly stretched light, redshift, from these ancient objects and analyze their spectra. Thus, the distance of Glass Z13 was estimated based on the absence of light in certain wavelengths, indicating absorption by the cosmic background radiation. The spectrum of Glass Z13 reveals a very low presence of heavy elements, reinforcing the idea that it belongs to an early phase of cosmic evolution. This aligns with the fact that elements like carbon, iron, and oxygen only appear after several generations of supernovae. In this sense, Glass Z13 may contain population 2 stars, or even offer indirect signs of the universe's very first stars, known as population 3, which have yet to be directly observed. Number 3. Active star formation in the Carina Nebula 7,600 light-years from Earth. The Carina Nebula is one of the most active stellar nurseries in our galaxy, located about 7,600 light-years away in the southern sky. When the James Webb Telescope observed this region, it revealed unprecedented details of star formation inside massive clouds of gas and dust. Known as NGC 3324, this area includes towering ridges, shock fronts, and emerging stars barely a few million years old. The resolution achieved by Webb allowed scientists to distinguish between gas structures and actual protostars within them. It's a glimpse into the chaotic beginnings of stellar life. What stands out most is the sheer level of texture in the images. The ridges and cavities are shaped by stellar winds and radiation from newborn stars, carving the surrounding material into pillars and arcs. These features, invisible in optical light due to dust, glow vividly in infrared. Webb's ability to peer through this dust is what makes its observations so unique compared to telescopes like Hubble. Entire regions that once appeared dark now reveal complex and active stellar dynamics. One of the most iconic views captured is the so-called cosmic cliffs, a wall of gas that looks like a jagged mountain range. But instead of stone, it's composed of hydrogen, helium, and various other elements. The edge of this structure marks the boundary where ultraviolet radiation from young, massive stars is pushing back the surrounding gas. This creates a contrast-rich region ideal for studying how stars form, evolve, and influence their environments. The image also highlights regions where jets and outflows from stars punch through the gas. Embedded within these dusty columns are protostars, objects in the early stages of stellar birth. Some are still accumulating mass, surrounded by circumstellar disks that may one day form planetary systems. Others are just reaching the point of nuclear fusion ignition, ready to shine on their own. Webb detected several of these objects using its NIRCam and MRI instruments, which are designed to identify warm sources and map their composition. These discoveries help refine models of how stars transition from cloud to flame. One of the most important contributions of Webb's Carina observations is the ability to measure temperature gradients within the gas. By analyzing these variations, scientists can better understand the conditions required for star formation. Not all dense regions collapse to form stars. The exact triggers remain an open question in astrophysics. Webb's data provides fresh insights by offering precise maps of where the gas is heating, cooling, compressing, or dispersing. It's a real-time view of stellar genesis. Some stars in this region are massive enough to influence the nebula's evolution dramatically. Their radiation generates winds that clear away nearby gas, while also triggering new rounds of collapse in adjacent zones. This feedback loop, where stars both form and destroy the conditions that allow formation, is central to how galaxies evolve. Webb's observations help visualize this process as it unfolds, highlighting the balance between creation and destruction within stellar nurseries. The chemical signatures picked up by Webb also revealed unexpected elements in the mix. Certain regions show concentrations of sulfur, neon, and complex carbon-based molecules, essential ingredients for future planetary systems. These materials are redistributed by supernovae and stellar winds over time, contributing to the cosmic recycling of matter. The presence of such compounds even in young star-forming zones hints at the early availability of life-building blocks in the galaxy. It's a key clue in the search for origins. Besides newborn stars, the Carina Nebula also hosts massive, mature stars nearing the ends of their lives. These include the enigmatic Eta Carina, a system so unstable and luminous that it's expected to go supernova relatively soon. The interactions between young and old stars within the nebula provide a natural laboratory for studying the stellar life cycle. Webb's infrared sensitivity allows researchers to track this interaction across time and space. With its incredible resolution, Webb detected fine jets of gas being ejected by forming stars, phenomena that were only theorized before. These jets help regulate the growth of protostars by shedding excess angular momentum and energy. Observing them directly allows astrophysicists to test long-standing models and update simulations of early stellar dynamics. Every detail adds to a more comprehensive view of how solar systems like our own might have formed. The ability to look at Carina in different infrared wavelengths also revealed hidden patterns of dust scattering and absorption. This helps scientists understand how light propagates through dense interstellar media, something crucial not only for star formation but also for interpreting other deep space observations. Knowing how dust interacts with radiation clarifies how energy moves through galaxies and how long it takes for stars to emerge. Webb's view of the Carina Nebula isn't just beautiful, it's scientifically dense. Each pixel contains layers of physical data, from velocity maps to molecular fingerprints. The combination of visual and spectral information enables researchers to decode this stellar nursery in ways never before possible. For the first time, we can watch star formation unfold, almost as if we were there, step by step, molecule by molecule. The Southern Ring Nebula, also known as NGC 3132, is located about 2,000 light-years from Earth in the constellation Vela. At first glance, it appears as a colorful, rounded cloud, but what we're really seeing is the last breath of a dying star. At its center lies a white dwarf, the remnant core of a once sun-like star that has shed its outer layers. The James Webb Telescope revealed those layers in remarkable detail, exposing fine structures and faint outer shells that were previously invisible. This nebula is a planetary nebula, a misleading name that has nothing to do with planets. The term comes from its round appearance in early telescopes. In reality, it's a bubble of ionized gas created when a star like our Sun runs out of fuel. The central star collapses under gravity, heating up and releasing ultraviolet radiation that excites the surrounding gas. Webb's infrared instruments captured this glowing shell from inside out, offering an intimate view of stellar death. What makes Webb's image unique is the clarity of the layers. Multiple concentric shells are visible, like the ripples of an explosion paused in time. These layers were formed during different stages of mass loss, and their spacing helps astronomers determine how fast the star was shedding material. Some layers are dense and bright, while others are diffuse, indicating slower or interrupted outflows. This depth of information gives new insights into how stars transition from red giant to white dwarf. A striking feature in Webb's view is the asymmetry of the nebula's structure. Unlike a perfect sphere, it has warped edges and directional flows, suggesting the influence of a binary companion. In fact, Webb confirmed the presence of a second star in the system, something only suspected before. This second star likely shaped the nebula's geometry, guiding how the dying star's gas was ejected. It's a powerful demonstration of how stellar interactions influence final outcomes. The central white dwarf itself is clearly visible in Webb's infrared images. It appears as a small, hot dot, the collapsed core of the original star, now cooling over billions of years. Observing this remnant provides a rare look at stellar physics under extreme conditions. These white dwarfs are supported by quantum pressure, and their temperatures, mass, and composition help scientists refine models of stellar interiors and nuclear fusion. Beyond the visible shell, Webb uncovered a halo of faint gas and dust surrounding the nebula. This extended material represents earlier mass loss episodes, possibly when the star was still in its red giant phase. Detecting it in infrared required the extreme sensitivity of Webb's instruments, particularly MIRI. By studying this halo, astronomers can reconstruct the timeline of the star's decline, much like reading tree rings to understand a tree's life. The nebula's composition also reveals its history. Spectral data shows high levels of hydrogen, helium, and trace elements like nitrogen and oxygen. These are the end products of nuclear fusion inside the star, now expelled into space. Over time, this material will mix with interstellar gas, contributing to the next generation of stars and planets. It's cosmic recycling on a grand scale. One star's death becomes the seed for new beginnings elsewhere. One of the major findings in this observation was the detection of complex carbon compounds. These molecules form in the cooler outer shells and can eventually become part of dust grains. Such compounds are thought to be the building blocks of organic chemistry in space. Webb's ability to identify them in planetary nebulae adds a new layer to the story of how life-friendly elements are spread throughout the galaxy. The dynamics of the nebula are also clearer now. Gas outflows appear to be moving at different velocities in different directions, influenced by the star's rotation and its binary partner. This directional shedding gives the nebula its non-uniform shape and helps explain why many planetary nebulae appear asymmetric. It's a phenomenon not easily observed in older data, but clearly visible in Webb's high-resolution mapping. The detailed velocity data also allows scientists to estimate the total mass lost during the star's final stages. For stars like our Sun, this can be up to 50% of their original mass. That mass is now floating as ionized gas in the nebula, a glowing record of stellar transformation. Measuring these values helps refine our understanding of how much material stars return to the galaxy over time. Unprecedented details of the pillars of creation in the Eagle Nebula M16. The pillars of creation are among the most iconic structures in space, located in the Eagle Nebula about 6,500 light-years from Earth. First made famous by the Hubble telescope in 1995, these towering columns of gas and dust stretch light-years in length. The James Webb Telescope has now revealed them in far greater detail using infrared light, allowing scientists to peer inside the dense regions where stars are forming. What once looked like solid shadows are now transparent clouds full of hidden activity. This view redefines our understanding of these structures. Webb's high-resolution infrared image shows that the pillars are not static or solid, but in constant flux. Radiation from nearby massive stars is slowly eroding them, while gravitational collapse creates new protostars within. Bright dots scattered along the pillars are these forming stars, some surrounded by disks of gas that may eventually form planets. The outlines of the columns are sharper than ever, revealing fingers, ridges, and flows shaped by radiation and turbulence. What was once visually impressive is now scientifically rich. The image also captures shock fronts, ripples of compressed gas triggered by stellar winds and ionizing radiation. These shock waves can either compress gas enough to spark new star formation or blow away material, halting the process. Webb's instruments allow scientists to measure the temperature and composition of these fronts in fine detail. This helps them understand whether these dynamic processes are constructive or destructive for future star birth. The pillars, then, become both cradles and battlegrounds for stars. A key advantage of Webb's view is its ability to detect early-stage protostars invisible in optical wavelengths. These very young stars are still gathering mass and often hidden behind dense dust clouds. With NIRCam and MIRI, astronomers identified dozens of such sources that Hubble could not detect. These protostars offer a snapshot of stellar infancy, a phase lasting only tens of thousands of years. Observing them is like catching lightning in slow motion. In addition to stars, the Webb image shows how material moves within and around the pillars. Gas and dust flow from the tips downward, forming streams that interact with surrounding material. This motion reveals how star formation isn't isolated, but part of a larger interconnected system. Each new star adds momentum to the nebula, influencing others nearby. It's a dynamic chain reaction visible in the textures and gradients within the image. The structures themselves, columns of hydrogen, helium, and interstellar dust, are shaped by radiation pressure. This erosion gradually transforms the pillars, a process captured in unprecedented time detail thanks to image comparisons with Hubble. The Webb data show changes that hint at how fast the structures are evolving. Although they appear motionless, the pillars are dissolving over time, suggesting that they will vanish within a few million years. Webb's spectroscopy also unveiled chemical gradients across the pillars. Some areas are rich in molecules like carbon monoxide and polycyclic aromatic hydrocarbons, PAHs, known precursors to organic chemistry. These compounds form in the wake of supernovae and stellar winds and can become part of planet-forming disks. Their presence in the pillars of creation suggests that the early conditions for planetary systems and potentially life are widespread in our galaxy. It's another piece of the puzzle of cosmic origins. Interestingly, the tips of the pillars contain higher concentrations of dense gas, where most protostars are located. These evaporating gaseous globules, or eggs, act as seeds for star formation, resisting the external radiation long enough to collapse under gravity. Webb's resolution enables astronomers to isolate and study these eggs individually. Each one tells a story of resistance and creation under extreme conditions. Their survival determines whether stars can form or not. Another layer of insight comes from polarization studies, which reveal magnetic field interactions in the region. Magnetic fields can support gas clouds against collapse or guide the direction of outflows from forming stars. Webb's sensitivity allows the mapping of these otherwise invisible forces. The shape of the pillars themselves may reflect underlying magnetic structures shaped over thousands of years. This adds complexity to the already intricate process of star formation. By comparing Webb's infrared image to older Hubble data, scientists can track the evolution of the region. New stars have appeared, shapes have changed, and brightness levels shifted. These comparisons provide a kind of time-lapse of cosmic evolution. It's a rare opportunity to observe how short-lived phenomena in astronomical terms can still be detected over a human lifetime. It brings motion and urgency to what was once thought eternal. The pillars of creation are not unique. Similar structures exist in other nebulae, but they are among the most studied due to their visibility and composition. Webb's data now make them a reference point for comparing other stellar nurseries. The principles learned here can be applied to regions farther away or more obscured. The pillars serve not only as a spectacular image, but as a universal laboratory for star formation. Orion Nebula, M42, cradle of forming planetary systems. The Orion Nebula, also known as M42, is the closest massive star-forming region to Earth, at about 1,350 light-years away. It's visible to the naked eye and has been observed for centuries. But the James Webb Telescope has opened a completely new window into its inner workings. By observing in infrared, Webb penetrated the thick dust that once obscured the heart of the nebula. Inside, it revealed hundreds of young stars, many surrounded by protoplanetary disks, early versions of what could become planetary systems. One of the key features of Webb's observations is the detection of proplids, short for protoplanetary disks. These are disks of gas and dust orbiting young stars, often distorted by nearby stellar winds. Some are already forming gaps that hint at planet formation in progress. Webb's sensitivity allows astronomers to measure their mass, temperature, and composition in detail. This is essential for understanding how planetary systems like our own come into existence. The Trapezium cluster, a group of massive stars at the nebula's center, plays a major role in shaping its environment. These stars emit intense ultraviolet radiation that carves out cavities in the gas and sculpts nearby proplids. The balance between this radiation and gravitational collapse determines which proplids survive long enough to form planets. Webb's data help clarify how this high-energy environment both triggers and inhibits star and planet formation. It's a complex, competing interaction. Webb's mid-infrared capabilities are especially useful for detecting warm dust in the inner parts of these disks. This allows scientists to track the formation of rocky materials, the building blocks of terrestrial planets. Some disks show signs of silicates and carbon-based compounds, similar to those found in meteorites. These materials are crucial for forming planetary cores and potentially for the development of life. The Orion Nebula thus becomes a model for studying early planetary chemistry. Another key discovery is the diversity among disks. Some are large and massive, while others are thin and dissipating quickly. Webb's spectral data show a range of compositions and temperatures, suggesting different evolutionary paths. Some systems may form gas giants, others may remain rocky and compact. This variety helps explain why exoplanets come in such a wide range of sizes and types. It also supports the idea that planetary formation is more chaotic than once believed. Webb also observed jets and outflows from young stars, revealing how angular momentum is managed in the earliest phases of system formation. These outflows shape the surrounding gas and often align with magnetic field lines. By studying their velocity and direction, scientists can infer the spin and growth rate of forming stars. This helps answer how stars avoid collapsing too quickly and how disks maintain stability during early development. Dust structures in Orion show layered shells and filamentary patterns, shaped by both internal and external forces. These patterns trace shock fronts, radiation pressure, and gravitational collapse. Webb's high resolution helps disentangle these effects, allowing clearer models of how material flows in a dense stellar nursery. Every pattern is a clue to the physical history of the region. Orion is no longer a vague glow in the sky, but a detailed map of cosmic engineering. The nebula also serves as a test case for star formation under intense radiation. Few regions in our galaxy combine such high-energy activity with high stellar density. This makes Orion ideal for testing theories of planet formation in extreme environments. Some proplids may never form planets due to photoevaporation, the process by which disks are eroded by nearby stars. Webb's data allow direct measurement of this process in action. Additionally, the Orion Nebula contains brown dwarfs, objects too small to become stars but too large to be considered planets. Webb identified several of these substellar bodies, adding to our understanding of the full spectrum of outcomes in star formation. Brown dwarfs occupy a mysterious space between categories, and their study can reveal insights into both stellar and planetary evolution. They show that not all clouds lead to stars, some remain in between. Molecules like water, methane, and carbon monoxide have also been detected in Orion's disks. These are crucial ingredients for prebiotic chemistry. Their presence so early in the formation process raises the possibility that the conditions for life begin before planets are even fully formed. Webb's spectrographs can identify these compounds with high precision, transforming Orion into a laboratory for astrobiology as well as astronomy. Colliding galaxies in Stephan's Quintet, 270 million light-years away. Stephan's Quintet is a compact group of 5 galaxies, 4 of which are gravitationally bound and interacting. Located about 270 million light-years away in the constellation Pegasus, it offers one of the clearest examples of galactic collision and merger processes. The James Webb Telescope captured the most detailed infrared image ever taken of this region, revealing shock waves, gas compression zones, and long tidal tails. These features are signs of intense gravitational interaction unfolding over millions of years. It's a rare, up-close view of galaxies in the act of transformation. One of the most dramatic elements in Webb's image is the shock front, stretching across hundreds of thousands of light-years. This structure forms where gas from one galaxy slams into intergalactic material at high speeds. The resulting compression heats the gas, producing X-rays and infrared radiation. Webb's instruments detected warm molecular hydrogen along this front, a tracer of energy dissipation and future star formation. This region may become a stellar nursery in the future. The quintet includes galaxies at different stages of interaction. Some are just beginning to distort under mutual gravity, while others show signs of tidal stripping and disruption. Stars and gas clouds are being pulled into intergalactic space, forming streams that trace the history of their motions. Webb's sharp imaging lets astronomers map these interactions in fine detail, helping to reconstruct the sequence of encounters. This data feeds into simulations of galactic evolution. One of the galaxies, NGC 7319, contains an active galactic nucleus, AGN, a supermassive black hole consuming matter at its center. Webb's mid-infrared data revealed dust-enshrouded regions surrounding the AGN, previously invisible. This helps scientists understand how black holes grow during mergers and how their energy output affects surrounding gas. Such feedback can trigger or suppress star formation depending on the environment. It's a key link in understanding galaxy-black hole coevolution. Another galaxy, NGC 7320, is not part of the actual quintet interaction. It only appears nearby due to line-of-sight projection. Webb's ability to resolve redshift differences makes it clear that NGC 7320 is much closer, about 40 million light-years away. This distinction is important for accurately modeling the dynamics of the remaining group. Misidentifying its distance in earlier studies caused confusion about the system's nature. Webb's spectroscopy corrects that. Star formation appears to be elevated in the overlapping regions between interacting galaxies. These compressed zones are ideal environments for collapsing gas clouds. Webb's data show strong emission lines from ionized hydrogen and other indicators of newborn stars. The interaction appears to be driving both destruction and creation. While old structures are torn apart, new ones are being born. This duality is typical of large-scale galaxy mergers. The quintet provides a scaled-down version of the processes that shaped massive elliptical galaxies in the early universe. Although these collisions happen over hundreds of millions of years, Webb's snapshot allows us to study each stage simultaneously. It's a natural time machine, offering glimpses of past and future galactic evolution. Each tail, bulge, and warped disk tells part of that story. The image is as instructive as it is striking. Tidal tails, long streams of stars pulled from galaxies, are visible in multiple directions. These structures are formed when gravity stretches stellar populations during close encounters. Over time, they can coalesce into dwarf galaxies or be reabsorbed into the larger host. Observing these features in detail allows astronomers to track how material migrates through intergalactic space. Webb's resolution helps measure the mass and composition of these tails with great accuracy. Dust lanes and dark regions across the galaxies reveal where gas is cooling and collapsing. Webb's infrared view can see through these dusty zones, uncovering hidden star clusters. These zones are often sites of intense starburst activity, where hundreds or thousands of stars form in a relatively short period. By comparing these features across different galaxies in the quintet, researchers can infer how environment shapes stellar outcomes. The variety of responses within one system is a valuable comparative tool. Because the galaxies are so close to each other, their halos of dark matter may also be overlapping. This interaction is thought to play a role in shaping their dynamics. Though dark matter is invisible, its presence can be inferred by the motion of stars and gas. Webb's observations, when combined with simulations, help refine estimates of how dark matter halos behave in dense environments. It's a step forward in understanding large-scale cosmic structure. The quintet has long been a target for multi-wavelength studies, including X-ray, radio, and optical observations. Webb's infrared capabilities add a crucial missing piece, especially for tracing warm gas and embedded star formation. When layered together, these datasets provide a complete portrait of how galaxies change over time. Each wavelength reveals a different piece of the puzzle, and Webb contributes the part that was hardest to see, the hidden and the hot. Overmassive galaxies in the early universe, CEERS 93316 and others. In the early data from the CEERS Cosmic Evolution Early Release Science survey, the James Webb Telescope identified galaxies that seemed too massive and evolved for their age. Among them, CEERS 93316 stood out as a candidate galaxy formed just 250 million years after the Big Bang. Its mass and brightness were unexpectedly high, suggesting either extremely rapid star formation or unknown astrophysical mechanisms. These findings challenge our current understanding of how quickly galaxies could have formed in the early universe. CEERS 93316's redshift is around Z approximately 16.7, among the highest ever measured. That puts it at a time when the universe was less than 2% of its current age. Yet its luminosity and apparent structure suggest a mature, massive system already in place. Such rapid assembly of mass contradicts existing cosmological models that predict a more gradual buildup. If confirmed, this galaxy, and others like it, may require revisions to theories about dark matter, cooling, and feedback. One possibility is that these galaxies formed through extremely efficient starburst episodes, converting vast gas reserves into stars in a short time. Webb's spectral data indicate relatively low metal content, which is consistent with young, first-generation stars. However, the organized structure and mass concentration are puzzling. Theoretical models struggle to explain how these features developed so quickly. More detailed observations are needed to confirm whether CEERS 93316 truly defies the timeline. Additional candidates, such as GLASS Z12 and CEERS 1749, show similar anomalies. Each displays brightness and redshift combinations that imply early and intense activity. The discovery of multiple such systems strengthens the case that the early universe may have been more complex than previously assumed. Rather than isolated anomalies, these galaxies could represent a common but previously undetectable class. Webb's deep field surveys are just beginning to uncover their prevalence. These galaxies raise important questions about the role of feedback mechanisms. Typically, radiation and stellar winds from early stars slow down further star formation. But in these objects, such processes appear to have been either delayed or bypassed. It's possible that environmental factors, like dense cosmic filaments or unusual dark matter concentrations, accelerated their evolution. Webb's continued observations may help determine what made these regions so exceptional. Another mystery lies in their morphology. CEERS 93316 appears more structured than expected for its time, possibly showing disk-like features. This suggests that galaxy organization into disks or bulges may occur earlier than thought. If disks could form so soon, theories about angular momentum conservation and gas cooling must be reevaluated. Webb provides the first real evidence to investigate this possibility. The presence of such massive galaxies so early could also affect estimates of cosmic reionization. These systems emit large amounts of ultraviolet light, which helps ionize intergalactic hydrogen. If many similar galaxies existed, they may have played a larger role in reionization than previously believed. Understanding this era is key to tracing the transition from the cosmic dark ages to a transparent universe. Webb data offer a new window into that transformation. To confirm their redshifts and masses, follow-up spectroscopic observations are essential. Some early estimates are based on photometric data, which can be misleading due to overlapping signals. Fortunately, Webb is equipped with NRSP, an instrument capable of high-precision spectroscopy. This will allow scientists to verify whether these galaxies truly exist at the reported distances, or if they are unusual but closer imposters. Even if some turn out to be less extreme than initially believed, their discovery reveals the incredible sensitivity of Webb's instruments. Just the fact that such objects were detected at all marks a new threshold in observational astronomy. We are now seeing galaxies in their infancy with clarity that was impossible before. This shifts the boundary of the observable universe closer to the moment of cosmic birth. Theoretical models are already being adjusted in response to these discoveries. Simulations like FIRE and Illustris are being recalibrated to match the observed properties of CEERS galaxies. These adjustments include faster gas accretion rates, alternative cooling scenarios, and new initial conditions. The dialogue between observation and theory is entering a new phase, with Webb pushing the conversation forward. The CEERS field was just one of several deep sky surveys planned for Webb's early operations. As more data comes in, astronomers expect to find dozens, possibly hundreds of similar overmassive galaxies. These will offer a statistical basis for redefining the timeline of galaxy formation. It's an exciting moment in cosmology, driven by direct evidence rather than speculation. Cosmic magnification through gravitational lensing in the SMACS 0723 cluster. Gravitational lensing occurs when massive objects, like galaxy clusters, bend the path of light coming from more distant sources. The SMACS 0723 cluster, captured in Webb's first deep field image, acts as a natural magnifying glass, warping and amplifying the light of background galaxies. This phenomenon allows astronomers to observe objects that would otherwise be too faint or distant to detect. In the Webb image, several arcs and elongated streaks are visible. These are galaxies stretched by lensing. It's a powerful reminder that space itself can function as an optical tool. Webb's infrared capabilities make it especially sensitive to high redshift galaxies, many of which become detectable only when lensed. In the case of SMACS 0723, multiple galaxies appear distorted into arcs due to the gravitational field of the foreground cluster. By analyzing the degree of distortion, scientists can estimate the distribution of mass, including dark matter, within the lensing cluster. It's one of the only ways we can see dark matter indirectly. These distortions become both a visual effect and a scientific measurement. The process of lensing also provides a rare opportunity to study galaxies from the early universe in greater detail. Some lensed galaxies appear 10 to 100 times brighter than they would without magnification. This allows researchers to examine their structure, composition, and star formation rates with unprecedented precision. Even the most advanced telescopes would not detect these objects without the gravitational assist. In essence, Webb boosts the reach of SMACS 0723 far beyond its technical limits. By measuring the position and shape of each lensed galaxy, astronomers can reconstruct the mass map of the lensing cluster. This includes both visible and invisible matter, making it one of the best tools for studying dark matter halos. The resulting mass distribution often shows discrepancies between where the light is and where the gravity is strongest, a signature of dark matter. These maps help refine cosmological models of how structure forms and evolves. Some of the most distant galaxies seen in SMACS 0723 are located behind the cluster, their light bent and duplicated by lensing. In some cases, a single galaxy may appear multiple times in the same image, in different locations and orientations. These multiple images are valuable for studying cosmic expansion and even time delay effects. Light takes different paths through space-time, so we see slightly different moments in the galaxy's history. It's a natural time machine with multiple windows. Webb's resolution allows for more precise modeling of these lensing effects than ever before. Each arc and image distortion is not just an artifact, it contains information about the intervening mass and the background source. Combining Webb's data with previous Hubble and ground-based surveys helps refine the lens models and confirm distance estimates. The synergy between telescopes adds depth to our cosmic understanding. Gravitational lensing can also be used to detect transient events like supernovae or variable stars in background galaxies. When such objects are lensed, their light curves can be amplified and observed for longer durations. In SMACS 0723, astronomers have already identified promising candidates for follow-up. These events may provide valuable information about stellar life cycles in the early universe. Lensing thus enhances not only spatial resolution, but also temporal accessibility. One notable lensed object in this field is a galaxy likely formed within 300 million years after the Big Bang. It would have been undetectable without the magnification provided by SMACS 0723. Its presence suggests that massive, structured galaxies were forming far earlier than predicted. This supports the emerging narrative that the early universe was more active and complex than once believed. Lensing provides the observational leverage to test these ideas. The lensing effect in SMACS 0723 isn't uniform. It varies depending on the location, mass distribution, and viewing angle. By mapping this variation, astronomers can build detailed gravitational potential models. These help predict where future lenses might be found and optimize future deep-field observations. Knowing where and how lensing occurs maximizes the scientific return of every Webb exposure. Beyond the science, the visual impact of gravitational lensing adds to the emotional weight of the image. Seeing galaxies stretched and duplicated across the sky evokes the fluidity of space-time and the scale of cosmic forces. These aren't camera distortions, they are actual fingerprints of gravity shaping light across billions of years. For many viewers, they're the first glimpse into the real flexible nature of the universe. Lensing also informs our understanding of cosmic expansion. The distances and redshifts involved in these images are critical for refining the Hubble constant. By comparing lensed and unlensed sources across cosmic time, scientists can detect subtle changes in the expansion rate. These insights feed into the ongoing tension between early and late universe measurements, a core question in cosmology today. A supernova captured in real time in the Pandora Cluster, Abell 2744. The Pandora Cluster, officially known as Abell 2744, is a complex region formed by the merger of at least 4 smaller galaxy clusters. Located about 3.5 billion light-years from Earth, it's rich in gravitational lensing and dynamic galactic interactions. When Webb observed this area as part of the Frontier Fields project, scientists identified a rare and fleeting event, a supernova in the act of fading. Capturing a supernova mid-event is uncommon, especially at such great distances. It marked one of the first real-time transient discoveries for Webb. The supernova, designated AT 2022 IRV, was spotted in a background galaxy behind the cluster. Its light was magnified by gravitational lensing, making the fading star visible from Earth. Webb detected it by comparing 2 exposures taken just days apart, which showed a significant change in brightness. This fading pattern is characteristic of a core collapse supernova, where a massive star ends its life in a dramatic explosion. The ability to catch this event on the decline is crucial for studying its physical properties. Observing a supernova during its fading phase allows scientists to measure the rate at which energy escapes from the explosion. The light curve, a graph of brightness over time, contains information about the star's mass, composition, and environment. In this case, Webb's instruments provided infrared data that is especially useful for viewing through interstellar dust. Many supernovae are hidden in visible light, but become clear in the infrared. This makes Webb an ideal tool for tracking such events. The supernova's light passed through multiple layers of matter, including the lensing cluster's dark matter halo. This journey caused delays and distortions in how the event appeared from Earth. Astronomers use these time delays to study both the supernova itself and the mass distribution in the intervening cluster. It's a dual measurement, telling us about both the exploding star and the fabric of the cosmos between us and it. Interestingly, this is not the only supernova detected in Abell 2744. Previous observations with Hubble had also revealed transient events, but Webb's sensitivity goes further. Its ability to see deeper and in finer detail increases the chance of catching these short-lived phenomena. Supernova evolve rapidly, often within days to weeks. Without timely data, many are missed entirely. Webb's success in this case sets a precedent for future real-time astrophysics. The galaxy where the supernova occurred is itself noteworthy. It lies far behind the cluster, and its light was stretched by redshift to near-infrared wavelengths. Webb's NIR-CAM and MIRI instruments were perfectly tuned to detect this light. By studying both the host galaxy and the supernova, astronomers can infer how stellar death proceeds in early or distant environments. This expands our catalog of known supernova types across cosmic history. Follow-up analysis of the spectra revealed elements like oxygen, iron, and silicon, classic indicators of core collapse processes. These materials are ejected into space, enriching the interstellar medium. Over time, they become raw material for new stars and planets. Supernova are thus essential engines of chemical evolution in galaxies. This single event, captured mid-fade, embodies that cycle. Lensing made this observation possible, but it also complicates interpretation. Multiple paths for light mean that parts of the explosion could appear at different times. Future images might even reveal a delayed echo of the same supernova. This time delay, measurable within days, is valuable for testing gravitational models and estimating the Hubble constant. Transients like these are gold mines for both stellar and cosmological science. The Pandora Cluster was specifically targeted for its lensing potential and history of transient events. Webb's success here validates that strategy and opens the door for similar campaigns. By monitoring high lensing clusters, astronomers can build a statistical sample of early universe supernova. This could reshape our understanding of stellar evolution at high redshift. It's not just a snapshot, it's part of a growing timeline. Real-time supernova detection also enables gravitational wave coordination. If a similar event were detected with Webb and LIGO Virgo, it could provide cross-verification for astrophysical phenomena. Though no gravitational waves were linked to this particular event, the possibility remains. Coordinated observations are the next step in multi-messenger astronomy. Active black hole at the center of galaxy NGC 7469. NGC 7469 is a luminous spiral galaxy located about 200 million light-years away in the constellation Pegasus. At its core lies an active galactic nucleus, AGN, powered by a supermassive black hole consuming matter at high speeds. The James Webb Telescope observed this galaxy using its mid-infrared spectrograph, MIRI, revealing structures hidden by dusk. Webb's data uncovered star-forming rings, warm molecular gas, and the inner workings of the AGN in unprecedented clarity. This makes NGC 7469 a key target for studying the link between black hole growth and galaxy evolution. The AGN in NGC 7469 emits intense radiation across the spectrum, but much of it is obscured by dust and gas. Webb's infrared vision allows it to pierce through this shroud and directly observe the dusty torus surrounding the black hole. This torus is where matter spirals inward before crossing the event horizon. The material heats up and emits strongly in the infrared, making Webb ideal for mapping its temperature and composition. The data suggest a dynamic, clumpy structure rather than a smooth, uniform ring. Surrounding the AGN is a prominent starburst ring, a region of intense star formation encircling the black hole at a distance of about 1,500 light-years. Webb detected complex feedback between the black hole and this star-forming region. Radiation and winds from the AGN influence how gas clouds collapse into stars, while star formation injects energy back into the environment. This creates a feedback loop where black hole and galaxy co-evolve. Webb's high spatial resolution lets astronomers study both processes simultaneously. MIRI's observations revealed strong spectral signatures of ionized neon, sulfur, and polycyclic aromatic hydrocarbons, PAHs. These markers help distinguish between energy from star formation and AGN activity. For example, PAHs are typically destroyed in the extreme environment near a black hole, but persist in star-forming regions. The ability to resolve these differences spatially within a single galaxy is a major advancement. It helps researchers map how energy flows across different scales. NGC 7469's black hole is estimated to be tens of millions of solar masses. Webb's data allow precise measurement of the accretion rate, how much matter is falling in over time. These measurements help refine models of AGN life cycles, which include active, quiescent, and reactivated phases. The current level of activity suggests NGC 7469 is in a peak accretion stage. Comparing this with galaxies in other phases can clarify what triggers black hole feeding episodes. Dust lanes traced by Webb reveal how material moves from the outer galaxy toward the center. Spiral arms act as highways for gas inflow, eventually feeding the AGN. Along the way, gravitational instabilities and star formation alter the composition of the inflowing gas. Webb's ability to track this flow in infrared helps explain how central black holes acquire their fuel. It also shows that galaxy structure plays a crucial role in black hole dynamics. The AGN's outflows, jets or winds of gas being expelled, are visible in the form of extended ionized regions. Webb detected these outflows pushing against nearby gas, creating shells and bubbles. These features affect how much star formation occurs in surrounding areas. In some zones, the outflows compress gas and trigger new stars. In others, they blow gas away and halt formation. Understanding this dual behavior is key to modeling galaxy evolution. Interestingly, some regions near the AGN show signs of recent supernovae. These may contribute to the gas dynamics around the core, adding energy and turbulence. Webb's data allow separation of these local stellar effects from the broader AGN impact. This multi-layered analysis is what makes NGC 7469 such a rich observational target. It offers overlapping processes at various scales. In addition to spatial structure, Webb observed variability in the AGN's infrared output. This may indicate changes in the accretion rate or the inner disk's structure. By monitoring NGC 7469 over time, astronomers hope to capture these fluctuations in action. Variability studies are crucial for understanding how black holes interact with their environment in real time. Webb's stability and sensitivity make it an ideal observatory for this kind of long-term monitoring. The broader implications of these observations are the confirmation that black hole growth and galaxy evolution are tightly coupled. NGC 7469 is a nearby example of this cosmic relationship, offering a detailed case study. Observing such interactions in distant galaxies is more difficult, so local systems like this serve as models. Webb's ability to dissect these interactions in high resolution makes the study even more impactful. These findings contribute to the growing realization that AGNs are not rare anomalies but common phases in galactic life. Many galaxies may pass through similar stages, shaping their structure and future star formation. NGC 7469, through Webb's eyes, demonstrates how a galaxy's heart can regulate its growth. It shifts the black hole from a mysterious singularity to a central architect of galactic history. Accretion signatures in black holes from the primordial universe. In the early universe, black holes were already growing rapidly, but how this growth began remains one of astronomy's biggest mysteries. The James Webb Space Telescope is now detecting signs of accretion in black holes that existed less than 1 billion years after the Big Bang. These primordial giants appear at the centers of ancient galaxies, emitting light from material spiraling into them. Webb's infrared sensitivity allows detection of these faint, distant objects through their energetic emissions and surrounding dust. It's our first detailed look at black hole feeding in the cosmic dawn. One of the key findings is the presence of active galactic nuclei in high redshift galaxies such as CEERS 1019 and GNZ 11. These AGNs emit strong mid-infrared signals, suggesting that accretion disks had already formed around early supermassive black holes. Webb's spectroscopy confirms that these emissions are not from stars, but from heated dust and gas being consumed. This provides direct evidence of rapid black hole growth in a time when the universe was still forming its first large structures. The masses of some of these early black holes are astonishing, hundreds of millions of times the mass of our Sun. Such size, so early, challenges models that rely on slow, steady growth from stellar mass seeds. Theories now include alternatives like direct collapse black holes or massive initial seeds formed from primordial gas clouds. Webb's observations support the idea that massive black holes may have formed very differently in the early universe compared to today. Accretion signatures also reveal the chemistry of the surrounding environment. Webb detected emission lines of ionized carbon, magnesium, and neon, products of early stellar evolution mixed with inflowing gas. These observations suggest that black holes and star formation were happening side by side. This complicates the idea of a quiet, isolated growth process. Instead, the picture is of a chaotic, dense environment where stars and black holes evolved in tandem. In some systems, the accretion disk shows signs of structure, variations in temperature, density, and speed. These patterns can be compared with simulations to estimate how efficiently the black hole is converting mass into energy. The results suggest that early black holes were accreting at or near the Eddington limit, the maximum rate before radiation pressure halts inflow. This means they were growing as fast as physics allows, explaining their rapid size increase. Dust surrounding the black holes emits infrared light, which Webb can trace to estimate mass inflow rates. In several cases, the dust geometry appears clumpy and asymmetrical, indicating irregular feeding. This uneven structure may result from turbulence, galaxy mergers, or interactions with nearby stars. Webb's resolution helps distinguish between these scenarios by analyzing how light is absorbed and re-emitted at different angles. Another important clue comes from time variability. Some of the early AGNs observed by Webb show changes in brightness over short periods. These fluctuations are consistent with shifts in accretion behavior, perhaps temporary blockages or bursts of material falling in. Monitoring these variations could offer new insights into black hole physics during their most active phase. It's a way of watching growth in action. Gravitational lensing plays a crucial role in detecting some of these faint AGNs. Foreground galaxy clusters bend and magnify the light from distant sources, making them visible to Webb. Several candidate black holes at redshifts beyond z=10 were identified this way. Lensing not only helps spot them, but also stretches their light over time, making temporal analysis easier. It's a fortunate amplification of some of the universe's most distant secrets. Webb's ability to distinguish between starlight and AGN light is essential in these studies. Without spectral analysis, bright galaxies might be mistaken for starbursts rather than black hole hosts. By separating these components, astronomers can better map where black holes reside and how common they were in the early universe. The data indicate that black hole growth was widespread, not confined to rare, special galaxies. These early accreting black holes may have influenced their host galaxies dramatically. Their energy output could heat surrounding gas, regulate star formation, and shape the galaxy's future structure. This feedback mechanism is already observed in nearby AGNs, but seeing it in the early universe is new. It shows that even at high redshifts, black holes were acting as galactic engines, not just passengers. The implications extend to cosmic reionization. Accreting black holes emit high-energy photons capable of ionizing hydrogen in the intergalactic medium. If numerous enough, they may have contributed significantly to the universe's transition from opaque to transparent. Webb's AGN discoveries help refine models of this key epoch, balancing the roles of stars and black holes in shaping early light. WASP-96b Detection of Clouds and Water Vapor in a Giant Exoplanet. WASP-96b is a hot gas giant located about 1,150 light-years from Earth in the constellation Phoenix. It's roughly the size of Saturn but orbits extremely close to its star, completing a full orbit in just 3.4 days. This makes it a prime candidate for atmospheric study, as its transit across the star allows light to filter through its atmosphere. The James Webb Space Telescope captured this filtered starlight with unprecedented detail, using its NIRIS spectrograph to produce a complete transmission spectrum. The result? Clear evidence of water vapor and the unexpected presence of clouds. Prior to Webb's observation, WASP-96b was believed to have a cloud-free atmosphere based on earlier Hubble data. This made it a useful control case for exoplanet atmospheric models. However, Webb's higher sensitivity revealed spectral features indicating cloud layers and a more complex atmosphere than predicted. The presence of water vapor absorption lines was unmistakable, marking the most detailed infrared analysis of an exoplanet atmosphere to date. It was also Webb's first official exoplanet result released to the public. The water vapor detected doesn't mean liquid water exists on WASP-96b. The planet is far too hot, with temperatures exceeding 1,000 degrees centigrade. Instead, it refers to water in gaseous form, seen in specific wavelengths as starlight passes through the planet's atmosphere. These wavelengths were absorbed in patterns that match water molecules. This measurement helps scientists study the composition, temperature, and cloud structure of alien worlds. Webb's ability to detect such signals opens the door to even more complex chemical discoveries in future observations. The detection of clouds was surprising because WASP-96b was long considered clear-skied based on its brightness and temperature profile. Webb's data showed muted spectral features, which is a common sign of clouds or hazes scattering light. These clouds may be made of silicates or other high-temperature materials, forming at altitudes where temperatures and pressures allow condensation. Understanding what kinds of clouds exist and how they form helps refine models of atmospheric circulation and chemistry on hot gas giants. Webb's high-resolution spectra allowed for precise measurements of atmospheric pressure layers. By analyzing how the water absorption changed with altitude, researchers could infer the vertical structure of the atmosphere. This three-dimensional view is critical for understanding how heat and radiation move through exoplanets. It also reveals how different atmospheric layers contribute to the planet's overall climate. WASP-96b now serves as a benchmark for modeling similar hot Jupiters. Studying this planet also improves our understanding of atmospheric opacity, the degree to which light is absorbed or scattered by gas and particles. The more opaque an atmosphere is at certain wavelengths, the more it hides deeper layers. WASP-96b's cloud coverage plays a major role in that opacity, affecting how we interpret all transit spectra moving forward. Even planets we thought were simple may be far more dynamic. Webb's tools offer a much clearer look through these obscuring layers. WASP-96b orbits a relatively bright star, which made it easier for Webb to obtain high signal-to-noise data. The star's light passed through the planet's atmosphere and into Webb's instruments during a transit lasting just a few hours. From this brief window, astronomers extracted rich chemical and physical information. The clarity and precision of the data validated Webb's promise as a revolutionary exoplanet observatory. The technique can now be applied to more complex or distant targets. The planet's tight orbit means it's tidally locked. One side always faces its star. This causes extreme temperature differences between the day and night sides, leading to powerful winds and potential thermal inversions. While Webb can't directly observe the weather yet, the atmospheric data hints at dynamic circulation patterns. Comparing absorption lines across the limb of the planet could eventually allow for mapping atmospheric movement. These are the first steps toward meteorology on alien worlds. WASP-96b's composition and cloud structure also have implications for planetary formation theories. The ratios of elements like oxygen, carbon, and water can reveal whether the planet formed close to its star or migrated inward. The presence of water vapor supports models suggesting this planet formed farther out and moved inward over time. This kind of chemical fingerprinting will be crucial for understanding the origins of exoplanets in diverse systems. Although WASP-96b is uninhabitable, the technology and methods used to study it are directly applicable to smaller, rocky planets. The goal is to eventually detect water vapor, carbon dioxide, methane, and even biosignatures in Earth-sized worlds. WASP-96b served as an early, ideal test case due to its size, brightness, and simplicity. What we learn from giants like this prepares us for studying more subtle, life-friendly planets later. The successful detection of clouds and water vapor in WASP-96b is also a triumph of calibration and precision for Webb's instruments. The smooth data curve and clear molecular signatures demonstrated the observatory's capabilities better than any theoretical test. It reassured scientists that the instruments could handle fine variations in light at interstellar distances. This performance is foundational to the mission's success. In essence, WASP-96b was never meant to be surprising, yet it delivered. The unexpected clouds, complex vertical layers, and robust water signals transformed it from a calibration target into a compelling scientific subject. Webb turned a seemingly ordinary gas giant into a milestone in exoplanet exploration. HD 189333b, the planet with blue sunsets and glass storms. HD 189333b is a gas giant located about 64 light-years from Earth, orbiting a star in the constellation Vulpecula. It's slightly larger than Jupiter and orbits its star every 2.2 days, making it an ultra-hot Jupiter. One of its most famous features is its deep blue color, not due to oceans, but because of atmospheric scattering and silicate particles. The James Webb Telescope revisited this iconic planet, building on previous Hubble and Spitzer data, to study its atmosphere in more depth. What it found confirmed earlier discoveries and added some fascinating new insights. One of the most visually striking aspects of HD 189333b is its sunset. Light scattering in its atmosphere causes the sky to appear blue, similar to Rayleigh scattering on Earth. But here, the effect is due to small silicate particles suspended in high-altitude winds. These particles also contribute to the planet's infamous glass storms, winds exceeding 5,000 miles per hour that may carry molten silicate droplets. Webb's infrared vision helps confirm the presence of such aerosols, linking optical and thermal observations. HD 189333b is tidally locked, meaning one side always faces its star while the other remains in darkness. This creates extreme temperature differences and fuels violent atmospheric currents. Webb detected phase-dependent variations in the infrared spectrum, suggesting complex heat redistribution mechanisms. Some heat flows from day to night side, but not evenly. Temperature maps show hot spots offset from the substellar point. This points to jet streams and chaotic wind patterns shaping the climate. The planet's deep blue color was confirmed not just visually but spectrally. Webb observed strong absorption features in the infrared, including signals from water vapor and carbon monoxide. These molecules help paint a full picture of atmospheric composition. The data also suggest the possible presence of hydrogen sulfide, a molecule linked to volcanic or chemical processes in gas giants. Each detection adds a piece to the puzzle of what this world is truly like. One of the more sensational aspects of HD 189333b is its glass rain, the idea that silicate particles condense and fall like molten glass. While Webb can't capture such weather events directly, the spectral data support the presence of silicate clouds at high altitudes. These clouds likely form in the hottest layers and rain down toward cooler zones. This exotic weather, combined with the blue hue and fast winds, makes HD 189333b one of the most alien places we've ever studied. Webb's observations also revealed temperature gradients across the planet's atmosphere. By analyzing emission spectra at different orbital phases, researchers could infer how heat is transported vertically and horizontally. These gradients affect cloud formation, atmospheric chemistry, and radiation balance. HD 189333b is becoming a model for understanding heat circulation in gas giants, both hot and cold. The data contribute to a growing archive of exoplanet climate systems. Webb confirmed the presence of haze layers that mute certain spectral features. These hazes complicate the task of identifying molecular signatures, but also provide information about atmospheric structure. The thickness, altitude, and composition of the haze influence how light is absorbed and scattered. Understanding these properties helps refine models of exoplanet atmospheres and can improve predictions for other similar worlds. The host star of HD 189333b is active and produces frequent flares, which can impact the planet's upper atmosphere. Webb's data show how the atmosphere responds to bursts of ultraviolet radiation. Such flares may strip away lighter elements or trigger photochemical reactions that create new compounds. This dynamic interaction between star and planet is a key focus of modern exoplanet research. HD 189333b's orbital geometry allows for both transmission and emission spectroscopy, giving a complete view of its atmosphere. This is rare among exoplanets and provides a dual perspective on composition and thermal structure. Webb's instruments can now capture these complementary datasets in higher resolution, revealing a level of atmospheric detail that was previously unattainable. It's like seeing both the silhouette and the glow of the planet at once. The data also showed strong signatures of wind-driven heat transfer. Shifts in spectral lines suggest that atmospheric material is moving rapidly across the terminator, the boundary between day and night sides. These flows contribute to temperature regulation and may carry molecules across hemispheres. Webb's ability to detect such motion in light-years distant worlds is a testament to its precision and stability. WASP-39b. Carbon dioxide confirmed in an exoplanet's atmosphere. WASP-39b is another hot gas giant located about 700 light-years from Earth, orbiting a sun-like star. It's larger than Jupiter and orbits extremely close to its host star, completing a year in just over 4 days. The James Webb Telescope used its NIR-SPEC instrument to perform the most detailed transmission spectrum of this planet's atmosphere. Among the most notable discoveries, Clear, unambiguous detection of carbon dioxide, the first time this molecule was confirmed in an exoplanet. This marked a historic achievement for atmospheric science beyond our solar system. The CO2 signature was seen as a broad absorption feature in the near-infrared spectrum, centered near 4.3 microns. This wavelength is difficult for ground-based observatories due to Earth's own atmospheric interference, making space-based detection essential. The strong signal left little doubt, confirming that carbon dioxide is present in significant quantities in WASP-39b's atmosphere. This validated long-standing models and demonstrated Webb's ability to detect key molecules linked to planetary processes and potential habitability. WASP-39b's atmospheric temperature is around 900 degrees Celsius, too hot for life, but ideal for infrared observations. Its large size and puffy atmosphere make it an excellent target for transmission spectroscopy. As the planet passed in front of its star, starlight filtered through its atmosphere, and Webb recorded how different wavelengths were absorbed. The result was a spectrum full of molecular information. The detection of CO2 added a crucial piece to the puzzle of exoplanet chemistry. The carbon-to-oxygen ratio in WASP-39b is now better constrained thanks to this observation. This ratio helps scientists determine where and how the planet formed in its protoplanetary disk. A high CO2 abundance suggests formation beyond the water ice line, followed by migration inward. This supports theories that hot Jupiters often form far from their stars and then shift closer. Webb's ability to derive this information from distant light is a major advancement in comparative planetology. In addition to CO2, Webb's data also hinted at the presence of other molecules, like water vapor and sulfur dioxide. These will be confirmed with follow-up observations using other instruments and at different orbital phases. The combination of multiple molecular detections allows for much more detailed atmospheric modeling. Each new compound provides clues about temperature, pressure, and chemical processes occurring in the atmosphere. WASP-39b is quickly becoming a reference planet for exoplanet science. Interestingly, the data also suggest the atmosphere may not be in chemical equilibrium. This means that vertical mixing, winds, or photochemical reactions could be altering the balance of molecules. Webb's detailed spectrum enables scientists to identify these departures from equilibrium and refine models accordingly. It moves the field beyond simple detection into dynamic, physics-based understanding. The planet is not just a point of light, it's a complex chemical system. WASP-39b's orbital geometry allows for frequent transits, enabling repeated and varied observations. This makes it ideal for testing time-dependent changes in its atmosphere. Future studies may examine how the composition shifts with temperature changes, star spots, or stellar flares. Webb's instruments are stable enough to track these small variations. This tracking may reveal new information about planetary weather, seasonal cycles, or photochemical dynamics. The CO2 detection is particularly important for the search for life. While WASP-39b itself is inhospitable, CO2 is a key molecule in terrestrial atmospheres, including Earth's. Its detection demonstrates that Webb can identify important atmospheric components even in faint, distant targets. This paves the way for future studies of smaller planets in habitable zones. The techniques used here will directly apply to systems like TRAPPIST-1 or potentially even Earth analogs. Another benefit of this observation was the opportunity to test different Webb instrument modes. Both the prism and grating modes of NIR-SPEC were used, showing consistent results across setups. This helped validate calibration pipelines and analytical techniques that will be used in all future exoplanet work. In this sense, WASP-39b wasn't just a target, it was part of Webb's commissioning phase, proving its readiness. The clarity of the CO2 signal also enables high-precision modeling of atmospheric pressure and temperature layers. This helps refine estimates of scale height, cloud coverage, and heat distribution. These parameters feed directly into global circulation models, which simulate climate systems on exoplanets. WASP-39b is becoming a foundational case study for atmospheric physics outside the solar system. LHS-475b is a rocky exoplanet located just 41 light-years from Earth, orbiting a red dwarf star in the constellation Octans. It's nearly the same size as Earth and completes a full orbit in only 2 days, making it a very hot world. The James Webb Space Telescope studied this planet using its NR-SPEC instrument, capturing data during 2 transits. These observations confirmed the planet's solid terrestrial nature, one of the few such detections outside our solar system. But the most exciting possibility, signs of a tenuous atmosphere. Webb's infrared transmission spectrum of LHS-475b was almost flat, meaning no strong molecular absorption was detected. This might suggest a lack of atmosphere, or that the atmosphere is composed of molecules that are hard to detect, like pure CO2. Alternatively, the planet could have a thin or patchy atmosphere, with sparse clouds or haze. While not a confirmation, the data leave room for further exploration. The findings made LHS-475b a top priority for follow-up studies. The planet's small size and rocky nature are critical because most of Webb's exoplanet detections so far involve gas giants. LHS-475b represents a new class of targets, potentially habitable rocky worlds, or at least their hotter cousins. Its proximity to Earth also makes it brighter and easier to observe repeatedly. These factors combine to make LHS-475b a stepping stone toward studying Earth-like planets in the habitable zone. It's the closest thing Webb has seen to a rocky Earth analog. The potential atmosphere could be composed of carbon dioxide, water vapor, or a mix of volcanic gases. If it exists, it would likely be thin and subject to intense stellar radiation due to the planet's proximity to its host star. This radiation may strip the atmosphere over time, so detecting any remnants is itself significant. Webb's precision allows researchers to model different scenarios and compare them against the observed spectrum. It's a slow but promising approach to decoding alien climates. Red dwarfs, like the one LHS-475b orbits, are known for stellar flares and variability. These can complicate observations by introducing noise into the data or actively affecting the planet's atmosphere. However, Webb's sensitivity allows researchers to isolate planetary signals from stellar interference. Future observations may look at different orbital phases to catch temperature changes or emission from the planet's night side. These techniques could offer further hints about surface and atmospheric conditions. Another advantage of LHS-475b is its short orbital period. This allows for frequent transits, making it easier to schedule multiple observations within a short time frame. Repeated measurements improve signal quality and reduce uncertainty. Scientists plan to use these frequent windows to build a more complete picture of the planet. Webb's long-term stability is ideal for such campaigns, gradually revealing details that would be impossible with less powerful telescopes. Detecting an atmosphere on a rocky planet is one of Webb's ultimate goals. While LHS-475b is too hot for life as we know it, it provides a proving ground for the techniques that will be used on cooler, potentially habitable exoplanets. By analyzing its faint signals, researchers refine their models and data processing methods. These advances will directly benefit studies of Earth-sized planets in systems like TRAPPIST-1. In this way, LHS-475b is helping shape the future of astrobiology. Interestingly, a completely flat spectrum is also valuable. It tells scientists what isn't there, ruling out thick hydrogen atmospheres or obvious biosignatures. This kind of negative result is key to narrowing down atmospheric models. It also forces the field to innovate, to push Webb's limits, enhance sensitivity, and create new ways of interpreting subtle patterns. In short, even silence can speak volumes in exoplanet science. The planet's surface conditions are still unknown, but models suggest extreme heat and possibly volcanic activity. If volcanic gases escape into the atmosphere, Webb might detect sulfur compounds or carbon monoxide in future observations. These would provide clues about geological processes on rocky exoplanets. For now, the planet remains an intriguing mystery, Earth-sized, but scorched and shrouded in uncertainty. Webb's observations of LHS 475b also validate the use of red dwarf systems for terrestrial planet hunting. These stars are smaller and cooler, so their planets block more light during transit, making spectral features easier to detect. Despite their flare activity, they may offer the best chance of detecting atmospheres around small, rocky worlds. LHS 475b is one of the first tests of this strategy, and it's showing promising results. The data from LHS 475b are still being analyzed and debated, but the early findings are encouraging. Even a whisper of atmosphere is an extraordinary discovery when dealing with planets only a few times larger than Earth's moon. The challenge now is to repeat and extend these observations, narrowing down the possibilities. If Webb can confirm a true rocky planet with an atmosphere, it will be a milestone in the search for life-supporting worlds. HD 189333b, the planet with blue sunsets and glass storms. HD 189333b is a gas giant located about 64 light-years from Earth, orbiting a star in the constellation Vulpecula. It's slightly larger than Jupiter and orbits its star every 2.2 days, making it an ultra-hot Jupiter. One of its most famous features is its deep blue color, not due to oceans, but because of atmospheric scattering and silicate particles. The James Webb Telescope revisited this iconic planet, building on previous Hubble and Spitzer data, to study its atmosphere in more depth. What it found confirmed earlier discoveries and added some fascinating new insights. One of the most visually striking aspects of HD 189333b is its sunset. Light scattering in its atmosphere causes the sky to appear blue, similar to Rayleigh scattering on Earth. But here, the effect is due to small silicate particles suspended in high-altitude winds. These particles also contribute to the planet's infamous glass storms, winds exceeding 5,000 miles per hour that may carry molten silicate droplets. Webb's infrared vision helps confirm the presence of such aerosols, linking optical and thermal observations. HD 189333b is tidally locked, meaning one side always faces its star while the other remains in darkness. This creates extreme temperature differences and fuels violent atmospheric currents. Webb detected phase-dependent variations in the infrared spectrum, suggesting complex heat redistribution mechanisms. Some heat flows from day to night side, but not evenly. Temperature maps show hot spots offset from the substellar point. This points to jet streams and chaotic wind patterns shaping the climate. The planet's deep blue color was confirmed not just visually but spectrally. Webb observed strong absorption features in the infrared, including signals from water vapor and carbon monoxide. These molecules help paint a full picture of atmospheric composition. The data also suggest the possible presence of hydrogen sulfide, a molecule linked to volcanic or chemical processes in gas giants. Each detection adds a piece to the puzzle of what this world is truly like. One of the more sensational aspects of HD 189333b is its glass rain, the idea that silicate particles condense and fall like molten glass. While Webb can't capture such weather events directly, the spectral data support the presence of silicate clouds at high altitudes. These clouds likely form in the hottest layers and rain down toward cooler zones. This exotic weather, combined with the blue hue and fast winds, makes HD 189333b one of the most alien places we've ever studied. Webb's observations also revealed temperature gradients across the planet's atmosphere. By analyzing emission spectra at different orbital phases, researchers could infer how heat is transported vertically and horizontally. These gradients affect cloud formation, atmospheric chemistry, and radiation balance. HD 189333b is becoming a model for understanding heat circulation in gas giants, both hot and cold. The data contribute to a growing archive of exoplanet climate systems. Webb confirmed the presence of haze layers that mute certain spectral features. These hazes complicate the task of identifying molecular signatures, but also provide information about atmospheric structure. The thickness, altitude, and composition of the haze influence how light is absorbed and scattered. Understanding these properties helps refine models of exoplanet atmospheres and can improve predictions for other similar worlds. The host star of HD 189333b is active and produces frequent flares, which can impact the planet's upper atmosphere. Webb's data show how the atmosphere responds to bursts of ultraviolet radiation. Such flares may strip away lighter elements or trigger photochemical reactions that create new compounds. This dynamic interaction between star and planet is a key focus of modern exoplanet research. HD 189333b's orbital geometry allows for both transmission and emission spectroscopy, giving a complete view of its atmosphere. This is rare among exoplanets and provides a dual perspective on composition and thermal structure. Webb's instruments can now capture these complementary datasets in higher resolution, revealing a level of atmospheric detail that was previously unattainable. It's like seeing both the silhouette and the glow of the planet at once. The data also showed strong signatures of wind-driven heat transfer. Shifts in spectral lines suggest that atmospheric material is moving rapidly across the terminator, the boundary between day and night sides. These flows contribute to temperature regulation and may carry molecules across hemispheres. Webb's ability to detect such motion in light-years distant worlds is a testament to its precision and stability. Spectrum of a dead star. Chemical remnants in a white dwarf. When stars like our Sun run out of fuel, they shed their outer layers and collapse into white dwarfs, compact stellar remnants roughly the size of Earth. These stellar corpses retain intense heat, glowing faintly as they slowly cool over billions of years. The James Webb Space Telescope recently observed one such white dwarf, providing a detailed spectrum of its surface composition. This data reveals chemical remnants left by previous planetary systems and offers insights into stellar death and the recycling of cosmic materials. The spectral lines detected by Webb showed strong absorption features of elements like calcium, magnesium, and iron on the white dwarf's surface. Typically, these heavy elements should sink deep into the star under its immense gravity within a short time frame. Their presence at the surface suggests they were deposited relatively recently by external sources, such as debris from asteroids or planets that ventured too close and were torn apart by tidal forces. This discovery implies the white dwarf has an active environment even after stellar death. The detection of rocky material at its surface confirms theories that planetary remnants often survive the death of their host stars. Studying these chemical signatures provides astronomers a window into the composition and structure of planetary systems that existed long ago. It also helps understand how planetary systems, including our own, might eventually meet their end. White dwarfs serve as cosmic archives, preserving the chemical fingerprints of their former planetary companions. Webb's spectroscopic analysis allows scientists to decode these fingerprints in detail. Different ratios of metals like silicon, iron, and magnesium hint at the types of rocky bodies that once orbited the star. This provides valuable comparative data for planet formation models and offers clues about the diversity of planetary systems across the galaxy. The star observed by Webb exhibited spectral features consistent with planetary debris rich in silicate minerals, similar to those found on Earth and in meteorites. This strongly suggests the presence of rocky planets or asteroids orbiting the star in the distant past. Such detailed evidence of planetary remnants is difficult to gather from any other method, making white dwarfs ideal laboratories for studying exoplanetary geology. Webb's detection also helps astronomers refine the age estimates of white dwarfs. As these stars cool, their spectral signatures change gradually, becoming simpler as heavy elements sink out of sight. Measuring how much metal remains visible allows for an estimate of how recently the debris arrived. Thus, the white dwarf spectrum not only reveals what happened, but also approximately when, providing a timeline of cosmic events around dead stars. The process of planetary engulfment and debris accretion around white dwarfs was previously inferred indirectly. Webb's detailed spectrum marks a significant advancement by providing direct observational proof. It confirms that the late stages of stellar life can be far more dynamic than previously assumed. Even long after a star dies, its gravitational pull continues to shape the destiny of surrounding planetary material. Observations like these help astronomers understand the ultimate fate of our own solar system. In about 5 billion years, the Sun will evolve into a red giant and eventually collapse into a white dwarf, potentially scattering and absorbing the inner planets. Studying current white dwarfs provides a preview of that distant future, helping scientists better model our solar system's eventual demise. Webb's infrared sensitivity played a key role in detecting these chemical signatures. White dwarfs are faint in visible light, but remain bright in the infrared for extended periods, enabling detailed spectral studies. By examining these long wavelengths, Webb uncovers hidden chemical compositions otherwise masked by surface cooling. This capability marks a new era in studying white dwarfs, significantly broadening the sample of observable stellar remnants. Further analysis of Webb's data may reveal traces of even more complex molecules and compounds. Such discoveries would indicate intricate chemical processes occurring within the debris disks surrounding white dwarfs. This could offer new insights into how complex organic chemistry might survive or evolve around stars that have ended their lives. It's a surprising potential habitat for molecular complexity. Ultra-distant galaxies detected in the deep infrared by CEERS. The Cosmic Evolution Early Release Science (CEERS) survey is one of Webb's flagship deep field projects, exploring some of the most distant galaxies ever observed. By peering into the infrared, Webb detected galaxies that formed less than 500 million years after the Big Bang, making them some of the earliest known structures in the universe. These ultra-distant galaxies provide essential insights into cosmic evolution, revealing how quickly and efficiently galaxies could form and mature. Among the ultra-distant galaxies discovered by CEERS, some exhibit surprisingly mature features, including organized structures and significant masses. This contradicts existing theoretical models that predict a slower buildup of galaxies in the early universe. These findings imply that galaxies could rapidly assemble, form stars, and become complex entities far earlier than previously thought. It's a profound revision of how astronomers view the cosmic timeline. One notable example from CEERS is CEERS 93316, a galaxy observed just 250 million years after the Big Bang. Despite its extreme age, Webb's data revealed signs of a structured morphology, indicating a level of complexity that traditional models struggled to explain. Such discoveries suggest that early galaxies might have formed via highly efficient gas accretion or mergers, requiring new theoretical frameworks to understand their rapid growth and evolution. Infrared observations are essential for studying these galaxies because the expansion of the universe stretches their ultraviolet and visible light into the infrared. Webb's specialized instruments, particularly NIRCam and MIRI, enable astronomers to detect this stretched light. The resulting images reveal galaxies previously invisible to telescopes working in shorter wavelengths. Webb thus provides the first clear view of these cosmic dawn objects. The discovery of these distant galaxies also enhances understanding of cosmic reionization, the period when the universe transitioned from opaque to transparent. Early galaxies, like those observed in CEERS, likely played a major role by emitting ultraviolet photons that ionized the surrounding intergalactic medium. By measuring their luminosity, astronomers can better estimate how much these early galaxies contributed to reionization, refining our cosmic timeline. Spectroscopic follow-up of CEERS galaxies will help confirm their redshifts and distances. Webb's NIRSpec instrument allows detailed examination of their chemical composition, star formation rates, and gas dynamics. Such analyses clarify the physical conditions within early galaxies, including their metallicity, how enriched they were by elements heavier than helium. These measurements offer critical insights into the early universe's chemical evolution. CEERS also challenges existing cosmological models regarding dark matter. The rapid assembly of massive galaxies so early in cosmic history suggests dense dark matter halos must have formed quicker than previously predicted. Understanding how these halos collapsed and formed is crucial for refining theories of cosmic structure formation, influencing future simulations and theoretical studies. The survey's detection of distant galaxies underscores Webb's extraordinary sensitivity. Galaxies billions of times fainter than what human eyes can see appear clearly in Webb's infrared observations. This capability sets a new standard for deep-field astronomy, allowing unprecedented access to the earliest epochs of cosmic history. Each new observation refines our picture of how galaxies and structures first emerged from primordial matter. CEERS galaxies also reveal varied evolutionary pathways. Some appear compact and starburst-driven, rapidly forming stars in dense clusters, while others show more diffuse structures. This diversity hints at multiple simultaneous pathways for galaxy formation, driven by different environmental factors and dark matter densities. Such variety suggests early galaxy formation was not a uniform process, but highly dependent on local cosmic conditions. These early galaxies are also laboratories for studying primordial stellar populations. Spectral analysis may reveal evidence of population 3 stars, the first generation of stars formed from pristine hydrogen and helium. Observing these stars directly remains challenging, but Webb's ability to detect indirect chemical signatures in early galaxies might offer crucial clues about their existence and properties. CEERS highlights how observational data can lead theory, prompting rapid advancements in cosmological simulations and models. Astronomers are actively revising assumptions about galaxy formation rates, star formation efficiencies, and gas accretion mechanisms in response to these discoveries. The dialogue between theory and observation has never been more dynamic, driven by Webb's groundbreaking capabilities. Complex organic molecules in protoplanetary disks, such as IRS-48. Protoplanetary disks are vast, rotating clouds of gas and dust surrounding young stars, nurseries where planets are born. IRS-48, a star located roughly 444 light-years away in the constellation Ophiuchus, hosts one of the most studied protoplanetary disks. The James Webb Space Telescope recently observed this disk and detected surprisingly complex organic molecules, significantly enriching our understanding of planetary formation. This discovery highlights the chemical diversity present even before planets fully form, shaping the building blocks available for future worlds. Webb's mid-infrared spectroscopy, MIRI, identified clear spectral signatures of organic compounds, including methanol and acetaldehyde, in the IRS-48 disk. These molecules are precursors to more complex organics, some even associated with life on Earth. Their presence in protoplanetary disks suggests the ingredients essential for potential life might be widespread, established long before planets themselves emerge. It sets the stage for the possibility that prebiotic chemistry is common across planetary systems. One fascinating aspect of the IRS-48 disk is its highly asymmetrical structure, with a prominent crescent-shaped concentration of dust and gas. This lopsided distribution is likely due to gravitational interactions, potentially indicating ongoing planet formation. Organic molecules concentrated in these dense regions may later incorporate into forming planets. Webb's data suggests planets born from such chemically rich disks might inherit abundant organic material, influencing their geological and atmospheric compositions. The detection of methanol, CH3OH, is particularly notable as it serves as a key molecule linking simpler chemicals to more complex organics. Methanol forms primarily on ice-coated dust grains deep within the disk. Webb's sensitivity enabled direct observation of these ice-covered grains, providing insights into how complex molecules form and evolve. It demonstrates that chemical complexity arises even in cold, dark regions of planetary merceries. Acetaldehyde, another organic molecule detected by Webb, is critical because it participates in reactions leading to sugars and amino acids, fundamental life-related chemicals. Finding such molecules within protoplanetary disks means the early stages of planet formation already set the stage for complex biochemistry. This doesn't guarantee life will develop, but it strongly suggests that the chemical prerequisites for life are abundant and common throughout the galaxy. These molecules were identified through infrared absorption features, which Webb measured with unprecedented clarity. Previous telescopes struggled with sensitivity limitations and interference from Earth's atmosphere. Webb's observations surpassed these issues, providing clear and direct evidence of complex organic chemistry. This allows astronomers to map precisely where such molecules are concentrated, significantly advancing our understanding of chemical diversity within disks. IRS-48's organic-rich regions align closely with dense dust traps, where grains accumulate and coalesce into planetesimals, the precursors to planets. This spatial correlation suggests a direct pathway from organic molecules to incorporation into larger bodies. Over millions of years, these organics could become integral to the composition of planets, moons, and comets, carrying life's building blocks far beyond their original stellar nursery. Further observations by Webb will investigate the chemical gradients across IRS-48's disk. Different molecules condense at specific temperatures and radii, producing distinct chemical layers. By mapping these layers, astronomers can reconstruct the disk's temperature and density structure, helping clarify how chemical diversity develops in protoplanetary environments. It is a detailed look into the chemistry behind planet birth. The implications of finding complex organic chemistry so early in planetary formation extend beyond IRS-48. It implies similar chemical processes may occur throughout many protoplanetary disks in our galaxy. If complex molecules are widespread, planetary systems throughout the universe may commonly start with the foundational ingredients needed for life. Webb studies provide crucial data for understanding how unique or common Earth-like chemical conditions might be. Additionally, Webb's findings inspire new theoretical models on disk chemistry, requiring reconsideration of how rapidly and efficiently complex organics form. Prior models underestimated the speed and scale of these chemical reactions. Now, astronomers must adjust these models to account for earlier and richer molecular diversity, profoundly impacting theories of planet formation and chemical evolution. The discovery of complex organics in IRS-48 also supports the notion that the chemistry leading to life on Earth might have originated even before our planet fully formed. Earth's chemical heritage could trace back to molecules in the primordial solar nebula, similar to those now seen around IRS-48. Understanding the conditions and processes in disks like IRS-48 thus informs our own origins, connecting distant stellar phenomena directly to life's fundamental chemistry. Distribution of carbon-rich and silicate cosmic dust. Cosmic dust, tiny particles composed mostly of carbon and silicates, is omnipresent throughout the universe. This dust plays a critical role in star and planet formation, influencing how material cools, condenses, and aggregates. Recently, the James Webb Space Telescope offered detailed observations of dust distribution across various cosmic environments, revealing new insights into the chemical composition, evolution, and behavior of interstellar material. The findings reshape our understanding of how cosmic dust drives the life cycle of stars and planetary systems. Webb's infrared capabilities are particularly well suited to studying dust, as infrared wavelengths easily penetrate regions that visible light cannot. By examining star-forming regions, planetary nebulae, and distant galaxies, Webb mapped the complex interplay between carbon-rich and silicate dust. These two primary dust types differ in how they interact with radiation, affecting star formation processes in unique ways. Webb's data thus provide detailed snapshots of cosmic dust's crucial role in galactic ecosystems. Carbon-rich dust typically forms in cool environments, often around dying stars like red giants, or in molecular clouds shielded from harsh radiation. Webb detected substantial carbon-based dust in regions surrounding evolved stars, highlighting how stellar deaths replenish the interstellar medium with organic rich materials. These carbon grains act as carriers for complex molecules, potentially aiding prebiotic chemistry wherever they accumulate, providing essential ingredients for future star systems. Silicate dust, composed primarily of silicon and oxygen, typically condenses around hotter environments, like supernova remnants or active star-forming regions. Webb's observations revealed fine details about silicate grain structures, identifying specific mineral compositions, such as olivine and pyroxene. Understanding these minerals helps scientists reconstruct the history of cosmic dust, tracing back to specific stellar sources and formation conditions, essential clues to galactic chemical evolution. Dust composition significantly affects star formation efficiency. Carbon-rich dust absorbs radiation differently than silicates, influencing how gas clouds cool and collapse. By precisely measuring dust distributions, Webb allows astronomers to refine models predicting where and how efficiently stars form. This has profound implications for understanding galaxy evolution, as star formation rates directly shape galaxy growth, structure, and the life cycle of cosmic matter. The distribution patterns observed by Webb showed stark differences between regions of active star formation and more quiescent areas. Active regions displayed increased concentrations of silicate dust, linked to energetic stellar activity and higher temperatures. Quieter regions favored carbon-rich dust, promoting colder, denser environments. This variation demonstrates how dust composition not only indicates the local environment, but actively shapes it, driving the very conditions that lead to stellar birth. Webb also provided unprecedented views of dust distribution in distant galaxies billions of light-years away. These observations revealed galaxies enriched with silicate dust earlier than expected, suggesting rapid chemical enrichment processes shortly after galaxy formation. Such rapid dust production indicates efficient stellar life cycles and challenges assumptions about early cosmic environments, pushing astronomers to reconsider how quickly galaxies can chemically mature. Additionally, Webb's observations traced the life cycle of dust grains as they travel through space. Dust formed in stellar atmospheres eventually disperses, mixes into interstellar clouds, and participates in new generations of star formation. By tracking dust across these stages, Webb provides comprehensive insight into how matter recycles through the galaxy, highlighting dust's essential role as a mediator of cosmic evolution and chemistry. Detailed infrared spectra from Webb also revealed dust grain size variations. These grain sizes influence optical properties, temperature regulation, and chemical reactivity. Smaller grains, for example, are more efficient at catalyzing chemical reactions essential for forming complex molecules. Understanding grain size distributions helps astronomers predict chemical diversity within star-forming regions, refining our understanding of molecular complexity's origins. Webb's findings also have implications for planet formation theories. Dust is the fundamental building block for planetesimals, eventually growing into planets. Variations in carbon and silicate distributions affect planet composition, from rocky terrestrial worlds to gas giants. By mapping dust compositions in different regions, Webb's data directly inform models predicting planet types and compositions, deepening our understanding of planetary diversity. These detailed dust observations encourage revised astrophysical models. Traditional simulations must now incorporate Webb's precise chemical and spatial information, leading to more accurate predictions of star and planet formation scenarios. This integration strengthens our theoretical frameworks, bridging gaps between observation and simulation to produce coherent pictures of cosmic dust's universal role. Traces of methane in HD 209458b, exotic chemistry in hot exoplanets. HD 209458b, also known as OSIRIS, is a hot Jupiter exoplanet orbiting its star every 3.5 days at just 7 million kilometers. This extreme proximity exposes the planet to intense radiation, causing its atmosphere to expand and escape into space. Using the James Webb Space Telescope, astronomers detected traces of methane in its upper atmosphere, an unexpected finding given the high temperatures. This discovery reveals complex chemical processes operating under extreme conditions. Methane, CH4, is typically unstable in hot atmospheres and was not expected to persist in such an environment. However, Webb's spectroscopic data revealed clear absorption features corresponding to methane's unique molecular signature. Its presence indicates that atmospheric chemistry on hot Jupiters may be more resilient or more dynamic than previously believed. It opens up new questions about chemical transport, shielding effects, and photochemical reactions in exoplanet atmospheres. The detection was made using Webb's NIRSPEC instrument, which measures the light filtered through a planet's atmosphere as it transits its host star. Subtle changes in starlight reveal which gases are present. Webb's high-resolution data allowed scientists to isolate methane's spectral signature despite interference from water vapor, carbon monoxide, and other gases. This level of clarity was unprecedented and represents a leap forward in exoplanetary spectroscopy. The atmospheric composition of HD 209458b also includes strong signals of water vapor and carbon monoxide. The interaction between these molecules under high heat and pressure may help explain methane's persistence. One hypothesis suggests that methane forms in deeper, cooler atmospheric layers and is transported upward faster than it can be destroyed by ultraviolet radiation. If true, this indicates powerful vertical mixing in the atmosphere. Another possibility is that localized clouds or hazes are providing temporary shielding from UV rays, allowing methane to survive longer. These clouds may be composed of exotic materials like silicates or metals, common in ultra-hot atmospheres. Such dynamic layering adds complexity to how astronomers model these worlds. Rather than simple gas envelopes, these atmospheres appear stratified and chemically rich. Methane is also a molecule of interest in astrobiology, often linked to biological activity. While no one assumes life on HD 209458b, the mere presence of methane under such harsh conditions forces a re-evaluation of the molecule's role as a biosignature. In extreme environments, methane might arise through entirely abiotic processes. Understanding these paths is critical for interpreting future detections in more habitable systems. The chemical profiles observed on HD 209458b challenge existing models of hot Jupiter atmospheres. Earlier simulations predicted methane would break apart almost instantly under such heat, yet Webb shows otherwise. This discrepancy implies gaps in our understanding of photochemical reactions and atmospheric circulation under exotic conditions. New models are being developed to account for these observations and better predict atmospheric chemistry. The detection also highlights the importance of continuous monitoring. Atmospheric composition can change over time due to stellar activity, weather-like patterns, or even orbit-induced tidal heating. Webb's ability to revisit targets and detect subtle temporal variations will be crucial for tracking how stable or volatile these exotic chemistries really are. The atmosphere of a hot Jupiter is not static. HD 209458b has long been one of the most studied exoplanets, even before Webb. It was the first planet where astronomers observed atmospheric evaporation and the first with detected water vapor. Adding methane to its chemical inventory gives scientists another layer of data for comparative analysis. It also makes the planet a benchmark for testing models of exoplanetary atmospheres. These findings have implications beyond HD 209458b. If methane can persist in one hot Jupiter, it might be present in others. Webb's ongoing survey of exoplanets will help determine whether this is a common feature or a rare anomaly. Each new detection or absence of methane will help refine the boundary conditions for its survival, shedding light on atmospheric processes across many planetary types. This also helps expand our understanding of exoplanet diversity. No longer can we assume that all hot Jupiters follow simple chemical patterns. Webb's data shows that even similar planets can host radically different atmospheres depending on subtle factors like metallicity, stellar type, and atmospheric dynamics. The diversity of chemistry is as rich as the planets themselves. WASP 76b, evidence of metal rain on an ultra-hot planet. WASP 76b is an ultra-hot Jupiter orbiting its star at such close range that one side always faces the star, locked in permanent daylight. The day side reaches temperatures around 2400 degrees Celsius, hot enough to vaporize metals. One of the most astonishing discoveries made by the James Webb Space Telescope was evidence that iron vaporizes on the day side and condenses into liquid metal rain on the cooler night side. It's a dramatic example of weather on a truly alien world. This extreme form of precipitation occurs due to the sharp temperature gradient between the day and night sides of the planet. On the star-facing side, metals like iron and possibly even titanium exist in gaseous form. Strong winds then carry this metal-rich vapor to the night side, where the temperature drops enough for the vapor to condense and rain down as molten metal. It's the first confirmed case of metallic rain in an exoplanet atmosphere. Webb confirmed this phenomenon by analyzing the planet's transmission spectrum during transit. Clear spectral absorption lines for iron and other metals were observed on the day side, but not on the night side, implying condensation. Additional modeling supported the idea that these metals don't simply vanish, they transition into liquid or solid forms and fall deeper into the atmosphere. It's a planetary weather cycle unlike any in our solar system. The concept of metal rain may sound fantastical, but it follows the same physical principles as water rain on Earth. When vapor encounters lower temperatures, it condenses into a liquid. In WASP-76b's case, the materials involved are radically different, but the process is familiar. This makes the planet a powerful analog for understanding atmospheric dynamics under extreme conditions. The planet's tidally locked nature creates permanent day and night zones, resulting in massive temperature differentials. Winds likely reach thousands of kilometers per hour, transporting gases across hemispheres. These winds are not just heat transporters. They also redistribute metals and alter atmospheric chemistry on both sides of the planet. The circulation patterns are crucial to maintaining this extreme metallic weather cycle. In addition to iron, there are hints of other metals such as vanadium, calcium, and titanium in vapor form. The presence of these elements further complicates the atmospheric chemistry and may lead to unique cloud formations on the night side. These clouds could consist of solidified metal particles, forming reflective layers or dense mists high in the atmosphere. It's a metallic meteorology in action. Understanding such atmospheres helps astronomers refine models of gas giant formation and evolution. WASP-76b's metallic-rich atmosphere challenges assumptions about how hot Jupiter form and retain their heavy elements. If metals are being rained out on the night side, it could lead to compositional changes over time. The planet may be chemically eroding or differentiating under the influence of its own weather. Webb's ability to distinguish day-night spectral differences is key to this discovery, by measuring subtle shifts in absorption lines during the planet's orbit. It reconstructs temperature profiles and identifies chemical transitions. This spatial sensitivity offers a more three-dimensional understanding of exoplanet climates. Instead of static profiles, we now see dynamic hemispheric systems unfolding in real time. One mystery is whether the metal rain reaches the planet's deep atmosphere or remains suspended in cloud layers. This has implications for energy balance and heat distribution. If metals fall deep into the atmosphere, they may absorb heat and affect internal temperatures. If they stay high, they could reflect starlight and cool the atmosphere more efficiently. Both outcomes influence the planet's long-term climate. The phenomenon also challenges assumptions about equilibrium chemistry. WASP-76b exists in a state of constant disequilibrium. Metals are continuously vaporized, transported, condensed, and recycled. This ongoing process must be modeled dynamically rather than as a steady-state system. Webb's data allows scientists to move beyond static theories and build more accurate atmospheric simulations. Comparing WASP-76b with other ultra-hot Jupiters will reveal whether metal rain is a common feature. Early data suggest similar processes may occur on planets like WASP-121b or Kelt 9b. These comparisons will help astronomers determine what factors, like temperature, metallicity, or atmospheric circulation, make metal rain more likely. Each planet offers a new piece of this strange puzzle. Planetary system forming in the protoplanetary disk of HL Tauri. HL Tauri is a young star located about 450 light-years from Earth in the constellation Taurus. It is surrounded by one of the most iconic protoplanetary disks ever observed, a structure of gas and dust where planets are in the process of forming. While ALMA first revealed HL Tauri's ringed structure in stunning detail, the James Webb Space Telescope has now provided even deeper infrared insight into the disk's composition and evolution. These observations confirm active planet formation is well underway. Webb's instruments detected thermal emissions from dust grains of various sizes, distributed in distinct concentric gaps and rings around HL Tauri. These features strongly suggest that forming planets are already carving out paths through the disk. The fine structure observed aligns with theoretical models where young planets gravitationally disturb their surroundings, clearing zones as they accrete mass. HL Tauri may host several planets in various growth stages. Using Webb's MIRI and NIRCam instruments, scientists analyze the disk's temperature and chemical gradients. These gradients influence where certain materials condense, shaping what types of planets can form in different regions. For instance, beyond the snow line, where temperatures drop low enough, ices like water and methane solidify, essential for gas giants. Webb's observations allow astronomers to pinpoint these boundaries with greater accuracy. One of Webb's most critical contributions was the detection of complex organics and silicate structures in the outer disk. These compounds are crucial in building both rocky and gaseous planets. The presence of crystalline silicates, in particular, indicates high-temperature processing, possibly from shocks or early planet-induced turbulence. Such processes are integral to shaping planets' mineral compositions and atmospheric characteristics. HL Tauri is extremely young, likely less than 1 million years old. The fact that its disk already shows signs of active planet formation suggests that planetary systems can begin to assemble rapidly after a star's birth. This challenges prior assumptions that planet formation takes many millions of years, forcing a reevaluation of early stellar and planetary evolution timelines. Some planets may form faster than we thought. Infrared data also revealed asymmetric features and clumps within the disk, which may be sites of localized accretion. These are areas where dust grains collide and stick together, forming larger bodies like planetesimals. Over time, these planetesimals can grow into full-fledged planets. Webb's sensitivity helps identify these clumps, offering a rare glimpse at the earliest stages of planetary assembly. Webb detected variations in gas density across the disk, suggesting that forming planets are influencing not just dust, but also the gaseous environment. These interactions are key to determining planetary orbits, masses, and eventual migration patterns. HL Tauri's evolving architecture may resemble a scaled-down version of what once occurred in our own solar system, giving clues to Earth's origin. Interestingly, Webb's data shows that some gaps in HL Tauri's disk are surprisingly clean, indicating large, possibly Jupiter-sized planets may be shaping them. Such massive planets forming so early raises questions about how quickly gas giants can accumulate enough mass before the disk dissipates. This forces scientists to revise models of planetary core accretion and gas envelope formation under time pressure. The overall disk appears to have a layered composition, with denser inner regions and more diffuse outer layers. This structure influences which elements are available for planet formation at different distances from the star. It also affects how heat is retained and radiated, shaping the thermal environment for emerging planetary bodies. Understanding this layering is critical for reconstructing a planet's chemical inheritance. Comparing HL Tauri to other protoplanetary systems observed by Webb shows significant diversity in disk structures. While some disks are smooth and symmetrical, HL Tauri's is more complex and active. This highlights that no two planetary systems form in exactly the same way. Webb's long-term mission will help build a statistical map of disk diversity and evolution throughout the galaxy. The HL Tauri system may also become a benchmark for studying planet formation across different environments. Its proximity, clarity, and active formation status make it an ideal laboratory for refining models and testing new predictions. By observing its changes over time, astronomers can watch planetary development unfold in near real time, an extraordinary opportunity in cosmic terms. Indirect evidence of population 3 stars in distant galaxies. Population 3 stars are the universe's first stars, massive, short-lived, and composed almost entirely of hydrogen and helium. They formed just a few 100 million years after the Big Bang and seeded the cosmos with heavier elements through their violent deaths. Despite their importance, no population 3 star has ever been directly observed. However, the James Webb Space Telescope may have found indirect evidence of their existence in several distant galaxies. One such clue comes from galaxies like GNZ 11 and CEERS 1019, whose light has traveled over 13 billion years to reach us. These galaxies exhibit spectral features that suggest an extremely low metallicity, meaning they lack heavier elements like carbon, oxygen, and iron. Such chemical fingerprints are expected from environments where population 3 stars dominated, before successive stellar generations enriched the interstellar medium. Webb's spectroscopic instruments captured unusually hard ultraviolet radiation in these early galaxies, consistent with the expected output from massive, metal-free stars. Population 3 stars are thought to burn hotter and more intensely than modern stars due to their pure hydrogen-helium composition. This would result in strong ionization of nearby gas, producing characteristic emission lines such as helium-2 at 1,640 angstroms, exactly what Webb has detected in some candidates. These emission lines are difficult to explain with normal stellar populations or active galactic nuclei. Their presence suggests that something more energetic and less chemically evolved is at play. While not definitive proof, the combination of low metallicity, extreme UV radiation, and helium emissions builds a compelling circumstantial case for population 3 influence. Webb may not be seeing the stars themselves, but it may be witnessing their aftermath. Another key observation involves the mass and brightness of these early galaxies. Some appear more massive and luminous than expected, indicating bursts of intense star formation. If population 3 stars formed in large clusters, their brief but powerful lifespans could explain this luminosity. Their supernovae would also rapidly enrich the surrounding medium, triggering the formation of the next stellar generation, population 2 stars. Webb's infrared range is ideal for probing these ancient galaxies because their light has been stretched by cosmic expansion. Earlier telescopes couldn't reach the wavelengths necessary to study this early epoch in such detail. Webb now allows astronomers to directly examine the light from when the universe was just a few % of its current age, bringing population 3 research into a new era of observational possibility. Theoretical models predict that population 3 stars had masses between 100 and 300 times that of the Sun. Such stars would explode in massive pair instability supernovae, leaving no remnant. These explosions would generate specific chemical patterns that could be detected in second-generation stars. Webb's high-resolution spectroscopy may help find such signatures, confirming population 3 influence through chemical archaeology. Some of the galaxies under study also show peculiar ratios of nitrogen and oxygen, consistent with theoretical predictions of early massive stellar nucleosynthesis. These chemical fingerprints act as fossil records, preserving information about stars that lived and died billions of years ago. Webb enables scientists to read these cosmic records with unprecedented clarity, scanning for clues in ancient starlight. The discovery of indirect population 3 evidence also informs our understanding of reionization, the era when the first light reionized the neutral hydrogen of the early universe. Population 3 stars, due to their intense radiation, are strong candidates for driving this transition. Webb's observations are helping to map when and how reionization occurred, narrowing down the timeline of cosmic dawn. While direct detection remains elusive, the hunt for population 3 stars continues. Webb will target more early galaxies in the coming years, looking for even stronger indicators of primordial stellar populations. With each new dataset, the likelihood of identifying definitive population 3 signatures increases, bringing us closer to confirming one of cosmology's oldest predictions. The eventual discovery, or absence, of population 3 stars has deep implications. If they are common, they shaped much of the universe's early structure and chemistry. If they are rare or absent, our models of early star formation may require significant revision. Either outcome represents a major leap in our understanding of cosmic origins. Cosmic web structure, matter intertwining distant galaxies. The large-scale structure of the universe is not random. Instead, galaxies and dark matter are organized into a vast cosmic web, a filamentary structure stretching across hundreds of millions of light-years. The James Webb Space Telescope has begun to reveal this architecture in unprecedented detail, detecting the faint light of distant galaxies as they trace the threads of the universe's invisible scaffolding. These filaments represent the paths along which matter clustered after the Big Bang. Simulations long predicted the existence of the cosmic web, but only now, with Webb's sensitivity, can we begin to see it in action. Galaxies do not form in isolation. They emerge where filaments intersect, drawn by gravity into nodes called galaxy clusters. Webb's deep field images show these intersections more clearly than ever, connecting galaxies into larger structures through subtle arcs of light and matter. It's a cosmic network shaping everything we observe. Using infrared light, Webb can peer through the dust that obscures other telescopes. This allows it to detect galaxies at extreme distances, helping astronomers trace the early formation of the cosmic web. The telescope's wide field of view and spectral capabilities also allow for redshift measurements, helping determine how far these filaments stretch in space and time. It's a map of the universe's skeleton as it was billions of years ago. Webb's data has also helped confirm that these filaments are composed not just of galaxies, but of gas and dark matter as well. Through gravitational lensing, astronomers can infer the presence of massive, invisible structures, bending light from background galaxies. These distortions align with the expected shapes of filaments, giving us a way to visualize dark matter's otherwise hidden role in structuring the cosmos. Some of the most detailed observations have come from studies of proto-clusters, regions where galaxy clusters are just beginning to form. Webb has detected faint halos of gas and stars stretching between early galaxies, forming embryonic versions of the vast structures seen today. These protofilaments are the earliest signs of cosmic connectivity, showing that the web began forming shortly after the first stars were born. By analyzing the temperature and chemical composition of gas along these threads, scientists are learning how material flows into galaxies over cosmic time. This accretion feeds star formation and galactic growth, acting like a river system nourishing islands in space. Webb can detect the spectral signatures of hydrogen, helium, and heavier elements within these threads, offering clues about how galaxies are built from the cosmic medium. Another striking feature of the cosmic web is its emptiness between filaments. These voids, immense regions with few or no galaxies, are just as important to the universe's structure. Webb's reach allows it to explore the edges of these voids, helping define the contrast between dense and empty regions. This contrast provides crucial tests for cosmological models and the role of dark energy in shaping space. Understanding the geometry of the cosmic web also informs us about the universe's evolution. The way matter clumps and spreads depends on both gravity and the expansion of space. Webb's observations allow scientists to test different models of cosmic inflation and large-scale structure formation. With each filament mapped, we refine our understanding of the fundamental forces at work in the cosmos. The cosmic web is not static, it's dynamic, with galaxies moving, merging, and evolving within it. Webb helps track this motion by measuring redshifts and Doppler shifts in light. These motions can reveal how galaxies migrate along filaments, fall into clusters, or get flung into intergalactic space. It's a living network, constantly reshaped by gravity and time. One of Webb's most fascinating findings is the alignment of galaxy spins with filaments. Some galaxies appear to rotate in directions that mirror the flow of matter along these threads. This suggests that the Webb doesn't just structure the cosmos spatially, it also influences the internal dynamics of galaxies. Such alignment could be a fossil record of the universe's earliest motions. The visualization of the cosmic web evokes both awe and scientific opportunity. It's the grandest structure we know, larger than any cluster, vaster than any supervoid. And yet, it's built from the interactions of fundamental particles and forces, scaling up from quantum fluctuations to galactic chains. Webb reveals this structure, not through imagination, but through light captured across the vastness of space. Ultimately, the cosmic web shows us that the universe is both interconnected and ordered. Galaxies, gas, and dark matter don't float in chaos. They follow patterns laid down in the earliest moments of existence. With each observation, Webb brings this invisible framework into sharper focus, helping us trace the threads that bind the cosmos together. Galaxies receding at velocities confirming accelerated expansion. One of the most profound discoveries in modern cosmology is that the universe is not just expanding, it's expanding at an accelerating rate. This conclusion stems from observing how galaxies recede from us, with more distant galaxies moving away faster. The James Webb Space Telescope contributes to this field by measuring redshifts with greater precision, confirming the trend predicted by the accelerated expansion model. It's a window into the universe's long-term fate. Galaxies recede due to the stretching of space itself, not because they are moving through space like rockets. As the universe expands, the light from distant galaxies is redshifted. Its wavelength is stretched toward the red end of the spectrum. Webb's infrared capabilities allow it to detect these redshifts, even from galaxies over 13 billion light-years away, pushing the boundaries of cosmic observation further than ever before. The relationship between distance and velocity, known as the Hubble-Lemaitre law, states that the farther away a galaxy is, the faster it appears to recede. Webb provides new data points at extreme distances, helping refine the slope of this relationship. These measurements are essential for calculating the Hubble constant, a value that determines the universe's expansion rate. Webb's precision adds clarity to a topic still surrounded by tension. That tension, known as the Hubble tension, arises because different methods yield slightly different values for the Hubble constant. Local measurements using supernovae and Cepheid variables give one value, while cosmic microwave background data suggests another. Webb's ability to observe galaxies from the early universe helps bridge these two approaches, offering intermediate data that might reconcile the difference or deepen the mystery. Some of the galaxies Webb has observed appear to be receding at velocities greater than 90% of the speed of light. This doesn't violate physics. It reflects the expansion of space itself, which can stretch faster than light across vast distances. These extreme velocities confirm predictions made by general relativity and support the existence of a repulsive force known as dark energy, thought to drive the accelerated expansion. Webb's spectroscopy allows scientists to identify characteristic emission lines from elements like hydrogen, oxygen, and nitrogen. By measuring how far these lines are shifted from their known positions, astronomers calculate each galaxy's redshift, and thus its velocity and distance. These observations are the foundation of our cosmic distance ladder, connecting brightness, time, and motion. In some observations, Webb has captured galaxies in the act of formation, when the universe was less than 1 billion years old. The speed at which these galaxies are receding reflects not only current expansion, but the cumulative history of cosmic inflation and dark energy. It's like reading the entire expansion timeline from light alone. Each photon tells a story of motion through expanding space. Webb's contribution also includes deeper surveys of galaxy clustering, revealing how galaxies move not only individually but as part of larger structures. Some clusters appear to be expanding apart, while others are gravitationally bound. These dynamics offer insight into the scale at which dark energy overtakes gravitational attraction. At the largest scales, expansion wins, and Webb is watching it happen. By observing galaxies in multiple wavelengths, Webb also provides information on their age and mass. These properties help calibrate expansion models by linking galaxy evolution with distance. More massive galaxies tend to form earlier, and their light helps probe earlier epochs. Webb's data makes it possible to build a continuous picture of expansion from the cosmic dawn to now. The expansion rate also has implications for the universe's destiny. If acceleration continues, galaxies will move ever farther apart, eventually fading from view. Webb gives us a glimpse into that future by showing galaxies already on the edge of detectability. Some of the light we see today left its source before Earth even existed, and that galaxy may now be moving beyond our observational reach forever. Cosmologists are also testing alternative theories, such as modified gravity or time-varying dark energy. Webb's precise data provides the empirical ground to test these models. Whether dark energy is constant or changing over time could reshape our understanding of the universe's ultimate fate, whether it expands forever, collapses, or tears apart. Tension between the local Hubble constant and cosmic background data. The Hubble constant defines the universe's rate of expansion, but measuring it has led to a major cosmological puzzle. Observations of nearby galaxies give a higher value than estimates based on the early universe, creating a discrepancy known as the Hubble tension. The James Webb Space Telescope offers critical data to explore this gap, acting as a bridge between local and primordial measurements. This tension could signal new physics or hidden flaws in our models. Locally, astronomers use standard candles like Cepheid variables and Type A supernovae to measure distance and velocity. These methods suggest a Hubble constant of around 73 kilometers per second per megaparsec. On the other hand, measurements from the cosmic microwave background, CMB, particularly from Planck satellite data, yield a lower value of about 67.4 kilometers per second per megaparsec. Both methods are precise, but their disagreement has persisted and even grown as data improves. James Webb refines the local method by observing Cepheid stars with greater clarity. Using its infrared capabilities, Webb penetrates dust that obscures optical telescopes like Hubble, providing cleaner luminosity measurements. These more accurate calibrations strengthen the local case, reinforcing the higher Hubble value rather than resolving the tension. Instead of narrowing the gap, Webb may be confirming that it is real. One suggestion is that the early universe behaved differently than we expect. If dark energy changed over time or new particles influenced early expansion, that could explain the discrepancy. Webb's observations of ancient galaxies and their clustering patterns allow scientists to test these ideas. They search for hints of altered physics like early dark energy or exotic neutrino species that might have influenced the universe's expansion history. Webb also helps re-express distances using gravitational lensing and surface brightness fluctuations, offering alternate methods to estimate the Hubble constant. These methods provide cross-checks, ensuring no single technique is skewing the result. So far, the alternate measurements have leaned closer to the local, higher value, deepening the mystery rather than resolving it. The tension is not just a statistical oddity, it could reflect a breakdown in the LCDM model, the standard framework of cosmology. That model includes dark energy, cold dark matter, and general relativity. If Webb's precise data continues to confirm a real discrepancy, cosmologists may need to modify or extend this model. The universe might be more complex than the current paradigm allows. One possibility is that we're missing some systemic error in Cepheid or supernova measurements. Webb helps rule this out by capturing multiple standard candles in distant galaxies and comparing their brightness across wavelengths. Its improved resolution and stability ensure that these observations are less prone to dust interference or crowding effects, boosting confidence in their reliability. Another hypothesis is that early universe estimates are skewed due to assumptions in the CMB analysis. These rely on interpreting temperature fluctuations from over 13 billion years ago, which involves complex models. Webb's intermediate redshift observations from galaxies formed a few billion years after the Big Bang fill the observational gap between CMB and local measurements, offering a new timeline to compare predictions against reality. Webb also aids in determining galaxy ages and star formation histories, which indirectly influence Hubble constant calculations. By knowing how fast galaxies formed and how long light travel to reach us, we can refine our understanding of cosmic timescales. These improved models could highlight where standard assumptions deviate from observed data, potentially revealing overlooked variables. Some propose more radical ideas, like varying fundamental constants or unknown interactions in the dark sector. These ideas would alter early universe behavior in subtle ways, but measurable ways. Webb's ability to gather high-fidelity spectra from ancient light sources enables detailed tests of such possibilities. Each new data point adds weight to or against these exotic theories. As more Webb data becomes available, cosmologists expect either convergence or deeper contradiction. If the Hubble tension holds firm, it could represent the most significant hint of new physics since the discovery of dark energy itself. The telescope is uniquely positioned to either expose unseen biases or confirm a fundamental gap in our understanding of the cosmos. Mapping dark matter through gravitational distortions in galaxy clusters. Dark matter is invisible, but its gravitational pull can be observed. One of the clearest ways to study it is by measuring how it bends light from background galaxies, a phenomenon known as gravitational lensing. The James Webb Space Telescope excels at detecting these distortions, enabling astronomers to map the distribution of dark matter in galaxy clusters with unprecedented resolution. It's like using light to trace the shape of the invisible. Massive clusters such as Abell 2744 and SMACS 0723 act like cosmic magnifying glasses. Their gravity bends the path of light traveling from more distant objects, warping and magnifying their images. These arcs and stretched forms reveal the underlying mass distribution, much of which is dark matter. Webb captures these subtle distortions in exquisite detail, making it possible to reconstruct the cluster's total mass. Using Webb's infrared sensitivity, scientists can observe faint background galaxies that other telescopes miss. The more distant the galaxy, the more dramatic the lensing effect appears. By analyzing how these galaxies are distorted depending on their position, astronomers reverse engineer the gravitational field that caused the effect. This process yields a 3D map of dark matter structures within the lensing cluster. Webb's precision enhances what earlier missions like Hubble began. While Hubble provided the first detailed lensing maps, Webb refines them with higher contrast and depth. It can see deeper into space and detect more subtle shifts in light, revealing small-scale clumps of dark matter that were previously undetectable. These fine structures help test the nature of dark matter itself. Different models of dark matter predict different behaviors. Cold dark matter, the standard model, suggests clumpy structures that form hierarchically. If Webb finds smoother or less concentrated distributions, this could support alternative theories like warm or self-interacting dark matter. By mapping enough clusters, Webb allows for statistical comparison between prediction and reality. One striking observation from Webb's early data is that dark matter does not always follow visible matter. In some cases, the gravitational center, inferred from lensing, does not align with the brightest galaxies in a cluster. This separation supports the idea that dark matter interacts only gravitationally, not electromagnetically, reinforcing its elusive, non-luminous nature. Gravitational lensing also helps identify substructures within galaxy clusters. These are smaller clumps of dark matter that haven't merged into the main halo. Tracking their locations and motions over time can tell us how clusters grow and evolve. Webb's repeated observations can build dynamic maps, revealing not just where dark matter is, but how it moves. Beyond mapping individual clusters, Webb contributes to cosmic shear studies, tiny distortions in the shapes of distant galaxies caused by large-scale dark matter distribution. By analyzing statistical patterns in millions of galaxies, scientists can infer how dark matter clumps across the universe. This contributes to understanding the role of dark matter in cosmic structure formation. Dark matter mapping also intersects with dark energy research. The growth rate of cosmic structures depends on the balance between gravitational attraction from dark matter and expansion driven by dark energy. By measuring how dark matter concentrations evolve over time, Webb helps constrain dark energy's influence. It's a delicate interplay shaping the entire cosmos. Some of the most ambitious projects involve combining Webb's data with X-ray and radio observations. Each wavelength traces different components: hot gas, stars, dark matter, providing a full picture of galaxy cluster composition. This multi-messenger approach reveals how baryonic matter interacts with the dark sector during mergers and collapse events. The ability to map dark matter with such clarity transforms it from a theoretical necessity into a mappable component of the universe. Webb doesn't see dark matter directly, but it exposes its presence through the unmistakable fingerprints it leaves on light. These maps are not just scientific tools, they are portraits of the unseen. Exoplanet GJ 1214b, shrouded in thick haze with unknown composition. GJ 1214b is one of the most intriguing exoplanets ever studied. Roughly 1.8 times the size of Earth, it's classified as a mini-Neptune, a type of planet not found in our solar system. Located just 48 light-years away, it has been observed extensively, but its atmosphere remained a mystery. The James Webb Space Telescope finally pierced the veil, revealing a thick, hazy shroud that resists easy classification. Previous observations from Hubble and Spitzer had hinted at a flat spectrum, meaning the planet's atmosphere wasn't letting any light through clearly. This suggested a dense layer of clouds or haze blocking the deeper layers. Webb's advanced infrared spectrometry gave scientists their first detailed look, but even then, the spectrum was dominated by a smooth, featureless profile. It confirmed the haze, but not what lies beneath it. Using its mid-infrared instrument, MIRI, Webb detected thermal emissions from the planet's day side. This allowed scientists to create a temperature map and infer some aspects of atmospheric circulation. GJ 1214b appears to be extremely hot, with temperatures around 230 degrees Celsius, but cooler than expected for a planet that close to its star. This implies the haze plays a major role in controlling heat. One theory is that the planet's atmosphere is composed of water vapor or even steam, possibly covering a liquid ocean or an icy core. Another possibility is a hydrogen-rich envelope with high-altitude photochemical hazes, similar to Titan's. Webb's observations lean slightly toward the latter, showing absorption features that may hint at methane or other complex hydrocarbons. Still, no conclusive molecular fingerprints have been confirmed. GJ 1214b orbits a red dwarf star, which emits less light than our Sun, but more energetic flares. These flares may continually reshape the planet's atmosphere, disrupting any stable chemical profile. Webb's data also show day-night circulation patterns that redistribute heat globally, possibly allowing the haze to form evenly around the planet, not just on one side. This uniform haze suggests a stable atmospheric layer at high altitudes, one thick enough to obscure all features below. The composition and pressure beneath this layer remain unknown. Webb's instruments can detect temperature differences, but they can't yet penetrate this fog. Future missions may be needed to uncover the deeper secrets of this planet's interior. What makes GJ 1214b especially fascinating is how it challenges classification. It's too massive to be a super-Earth, too small to be a Neptune, and too hazy to decode easily. Webb shows that the universe holds many planetary types unlike anything in our solar system. These worlds may be common. GJ 1214b could be one of billions. Understanding GJ 1214b's atmosphere could help explain the formation and evolution of mini-Neptunes. Are they failed gas giants, evaporated ocean worlds, or a third category altogether? Webb's insights are just the beginning of unraveling that mystery. By studying heat flow, albedo, and emission spectra, scientists are piecing together the planet's hidden identity. The planet's relative proximity makes it a perfect target for long-term study. Repeated observations with Webb and next-generation telescopes will help track changes in haze, chemistry, and temperature. If these variables shift over time, it could indicate active weather, atmospheric escape, or chemical cycling. The planet becomes a dynamic laboratory for exoplanet science. Webb's success in mapping GJ 1214b's heat signature, even without penetrating the haze, marks a milestone in exoplanet characterization. It proves that even challenging targets can yield valuable data. The mission pushes boundaries in what we can learn from indirect observation, especially in worlds so different from Earth. Discovery of metal-rich stars in the early universe. For decades, astronomers believed the first stars in the universe contained almost no metals, elements heavier than helium. These population 3 stars were thought to be massive, short-lived, and composed of primordial material. But James Webb's observations have uncovered a surprising twist. Galaxies in the early universe already hosted stars rich in metals, suggesting rapid chemical enrichment soon after the Big Bang. Webb's powerful infrared instruments allow it to see galaxies as they were just 500 to 700 million years after the Big Bang. Within these galaxies, scientists detected spectral lines corresponding to elements like oxygen, neon, and even iron. This implies that previous generations of stars had already lived, died, and seeded the cosmos with heavier elements, far earlier than expected. These metal-rich stars challenge the idea that early galaxies were chemically primitive. Some of the galaxies observed, like GNZ11 and those in the CEERS and GLASS surveys, show metal abundances comparable to or exceeding those in modern dwarf galaxies. This suggests that massive star formation and supernova-driven enrichment happened at breakneck speed during the universe's infancy. Webb detects these signatures through emission lines, bright wavelengths produced by hot gas surrounding young stars. The presence of metals alters the way gas cools and forms stars, influencing both galaxy evolution and star mass distribution. The higher the metallicity, the more efficiently gas can radiate away energy, forming smaller and longer-lived stars. One mystery is how such rapid enrichment occurred. The early universe was chaotic, with galaxies forming through frequent mergers and inflows of pristine gas. These processes may have triggered intense starbursts, where generations of stars were born and died in rapid succession. Supernovae from massive stars would then expel metals into surrounding space, enriching future generations. Webb also found that metallicity varied within single galaxies. Some regions showed high concentrations of metals, while others remained nearly pristine. This patchiness reveals the complex internal dynamics of early galaxies, mixing processes, starburst zones, and areas shielded from feedback. It paints a picture of galaxies in chemical flux, rather than smooth evolution. These findings reshape our timeline for cosmic chemical evolution. Instead of a long dark age followed by slow growth, it appears that many galaxies reached high metallicity within the first billion years. This has profound implications for our understanding of early star formation, supernova rates, and the formation of rocky planets. If metals were abundant early on, then the ingredients for planet formation, carbon, oxygen, silicon, were also in place. This raises the possibility that planetary systems and even life-friendly environments could have existed in the universe's first few billion years. It pushes the potential window for habitability much further back than previously thought. Webb's spectral sensitivity also allows scientists to distinguish between different enrichment processes. Some galaxies show signs of enrichment from Type II supernovae, while others bear the fingerprints of Type A explosions, implying even more time had passed. These distinctions help trace the age and mass distribution of early stellar populations. Another exciting aspect is the role of early quasars. These active galactic nuclei can accelerate chemical enrichment by triggering star formation and driving outflows that mix elements. Webb's dual observations of quasars and surrounding galaxies provide insight into how black holes might have influenced early galactic chemistry. The discovery of metal-rich stars at high redshifts supports a new view of cosmic history, one in which the universe matured faster than expected. Instead of a long dark age followed by slow growth, it appears that complexity emerged rapidly. The universe wasted no time in building the elements of stars, planets, and potentially life. Triple System TIC 4707-10327 is a rare triple star system that defies current models of stellar dynamics. Located roughly 1,900 light-years away, it contains 3 stars tightly bound and an unusual orbital configuration. What makes this system remarkable is that the inner binary orbits one another every 1.63 days, while a third star orbits both every 52.8 days, an arrangement that shouldn't be stable under current models. James Webb didn't discover this system, but its instruments provided crucial follow-up data to characterize its components more precisely. Using its infrared capabilities, Webb could isolate the spectral signatures of each star, determine their temperatures, masses, and compositions, and detect any perturbations in their motion over time. This deepened the mystery. The system shouldn't be dynamically stable, yet it persists. In typical triple systems, wide outer orbits help avoid gravitational instability. But TIC 4707-10327 has unusually tight separations and near coplanar orbits. Simulations show such systems should destabilize rapidly unless finely tuned. Webb's data confirmed that this is not a fluke. TIC 4707-10327 is real, and it's not falling apart. This forces astrophysicists to reevaluate how such systems can form and persist. One possibility is that the system formed through disk fragmentation in a massive protostellar disk. In such cases, gravitational instabilities can create multiple stars from the same rotating structure. However, even this model struggles to explain the observed orbital alignment and compactness. Webb's observations provide detailed temperature and metallicity measurements, hinting that all 3 stars share a common origin. Another idea is that a fourth star once existed but was ejected through a close encounter, tightening the remaining orbits. This kind of dynamical interaction could leave signatures in the current orbit's eccentricities or inclinations. Webb's high-precision photometry allows astronomers to search for such irregularities. So far, no evidence of a past ejection has emerged, but the search continues. TIC 4707-10327 also contributes to understanding stellar evolution in multi-star systems. How do stars exchange mass or angular momentum in such tight configurations? Webb's spectroscopy helps monitor emission lines associated with stellar winds, accretion flows, and magnetic activity, clues to the internal dynamics that may stabilize or destabilize the system. The inner binary, being so close, likely experiences tidal interactions that synchronize rotation and orbit. These effects can dissipate energy and lead to long-term orbital changes. Webb's ability to track light curves and spectral shifts across time gives scientists a window into these slow processes, offering clues about the system's future evolution. TIC 4707-10327 also may host planets, although none have been detected yet. If found, such planets would face extreme gravitational environments, with shifting stellar illumination and variable tides. Webb's infrared sensitivity makes it well-suited to search for transits in such systems, even with the complicating factor of 3 host stars. Triple systems like this are critical for testing models of stellar formation. They are nature's laboratories for gravitational dynamics, accretion processes, and even relativistic effects. TIC 4707-10327, in particular, offers a unique setup where small perturbations can yield large theoretical insights. Astronomers are also using machine learning to scan through massive datasets for similar systems. Webb's confirmed observations of TIC 4707-10327 serve as a training benchmark for these algorithms. The better we understand this outlier, the more likely we are to discover others and perhaps refine or rewrite our theories. What we see in TIC 4707-10327 is more than a curiosity. It's a challenge, a signal that our current models are incomplete. Thanks to Webb's precision, we now have enough information to explore these dynamics in detail, and that could reshape how we think about the architecture of stellar systems across the galaxy. Isolated spiral galaxy in the Botez void. The Botez void is one of the largest known empty regions in the universe, a cosmic desert nearly 330 million light-years across, containing far fewer galaxies than average. Within this vast emptiness, astronomers discovered a lonely spiral galaxy, catalogued under various designations, but known for its isolation. Webb's instruments offered the first detailed look at this solitary system, raising questions about how it formed and survived in such an empty place. Spiral galaxies typically form in dense cosmic environments, where gravitational interactions and gas accretion promote disk formation and starburst activity. Finding one thriving in a void defies these expectations. This galaxy has maintained its structure, complete with spiral arms, a disk, and active star formation, despite lacking neighboring galaxies for support or merger history. Webb's deep imaging confirms this structure in exquisite detail. The galaxy's redshift places it deep within the Botez void, confirming that it isn't just a foreground object. Webb's infrared view reveals cold gas lanes and dust structures that trace recent star formation. Spectroscopic data show emission lines from young hot stars, including hydrogen alpha and oxygen, typical markers of ongoing stellar birth. The galaxy may be lonely, but it's alive. One surprising feature is its metallicity, which appears comparable to galaxies in normal environments. This implies that either the galaxy formed quickly after the void itself and has sustained internal star formation for billions of years, or that it once belonged to a denser region before drifting into isolation. Webb's precision helps test both possibilities through stellar population analysis. By examining the galaxy's outer halo and stellar age gradients, scientists aim to reconstruct its migration history. If stars in the outskirts are younger or more metal-rich, that could suggest later gas inflows or minor mergers. But so far, data suggest a steady internal evolutionary path, making this galaxy an example of self-contained galactic development. The galaxy also shows signs of a central bulge and possible weak bar structure. These features often emerge from internal disk instabilities, not external interactions. Webb's data allow astronomers to model how such features might evolve in isolation, without gravitational nudges from companions. It's a study case of pure, unperturbed galactic evolution. Its location in the Botez void also makes it a unique test case for theories of large-scale structure formation. How did enough matter accumulate in this part of the universe to form a spiral galaxy? Did it condense from primordial filaments that later expanded outward, leaving it stranded? Webb's wide-field context imaging seeks to trace any nearby filaments or small galaxies. Isolated galaxies are valuable for calibrating models of cosmic variance. They help determine whether certain features, like spiral arm pitch angles, star formation efficiency, or gas retention, are shaped by environment or intrinsic properties. Webb's multiband observations of this galaxy give us a clean baseline, untainted by environmental effects. There are also implications for dark matter distribution. If the galaxy retained its disk and dark matter halo in such a low-density area, it might suggest more resilient halo structures than previously thought. Webb's gravitational modeling through stellar motions and rotation curves will help probe the extent and shape of its dark matter envelope. The Botez void itself remains a mystery. Its existence challenges the idea of uniform matter distribution on large scales. Galaxies like this one are rare windows into how the universe's structure was seeded and grew. Webb helps fill in that emptiness, not with matter, but with meaning. Image sequence of cosmic evolution, from the Big Bang to present-day galaxies. The James Webb Space Telescope offers more than snapshots. It delivers a timeline. Through its deep field and spectroscopic observations, Webb reconstructs the universe's evolution, capturing key stages from the aftermath of the Big Bang to the mature galaxies we see today. Each image isn't just a picture, it's a point on a cosmic timeline spanning over 13.8 billion years. Webb's infrared capabilities allow it to see ancient light stretched by the expansion of space. The most distant galaxies it detects appear as they were just 300 to 500 million years after the Big Bang. These galaxies are small, irregular, and forming stars at incredible rates. They're the early building blocks of cosmic structure, primitive yet essential. Next in the timeline, Webb reveals galaxies in transition. Around 1 billion years post-Big Bang, galaxies began to assemble into more stable forms. Disks, clumps, and nascent spiral arms appear. Star formation is still rampant, but dust begins to accumulate. Webb captures this phase with unprecedented detail in fields like CEERS and glass. Moving forward, between 2 and 4 billion years, galaxies grow more complex. Mergers become common, reshaping their structure and triggering bursts of star formation. Webb's images show galactic collisions frozen in time, twisting spirals, disrupted cores, and tidal tails. These interactions help galaxies evolve, mix their contents, and form heavier elements. Webb also traces the rise of quasars, supermassive black holes at galactic centers. At redshifts around 6 to 7, we see brilliant, compact sources powered by rapidly feeding black holes. These early quasars illuminate their surroundings, ionizing gas and altering galaxy growth. Webb spectra decode their chemical makeup, mass, and energy output. At around 5 to 8 billion years, galaxies begin to resemble those we know today. Spiral structures, stable disks, and ordered rotation emerge. Webb captures dust lanes, star clusters, and even galactic bars. Metallicities increase as generations of stars live and die. The universe enters a phase of quieter, more balanced evolution. Webb's observations also reveal the large-scale structure of the universe. Vast cosmic webs of dark matter and gas connecting galaxies across space. Some images show filaments and voids, tracing the hidden scaffolding of the cosmos. This framework underlies everything we observe, guiding galaxy movement and clustering. In the more recent universe, Webb observes galaxies with fully developed morphology. Giant ellipticals, barred spirals, and dwarf galaxies populate these later epochs. The rate of star formation declines, but activity continues in bursts. By comparing older and younger galaxies, Webb helps reconstruct how individual systems matured over billions of years. Through time-lapse-like sequences across redshifts, scientists build evolutionary models. By aligning galaxies by age and morphology, they simulate growth histories, mergers, and chemical evolution. Webb's precision allows for comparisons across epochs, building a virtual film reel of galactic life from infancy to maturity. In one remarkable composite, Webb's deep field shows galaxies from multiple eras in a single frame. Some are less than 1 billion years old, others are over 10 billion years. Each dot is a separate chapter in cosmic history. The further the light has traveled, the further back in time we're looking, layering space with time. This visual sequence also helps refine cosmological parameters. By measuring distances, masses, and star formation rates over time, Webb contributes to more accurate models of universal expansion. It even aids in calibrating the Hubble constant and testing the lambda CDM model, the current framework for dark energy and matter. In essence, Webb provides a moving image of the universe's growth, not in real time, but through time itself, by catching ancient light frozen on its way to us. These sequences remind us that the cosmos is not static, it's a living history, and every image from Webb is a frame in a film that began 13.8 billion years ago.